At the very core of our galaxy, hidden behind dense clouds of gas and dust, lies a force so immense it bends time and space itself. Sagittarius A, the supermassive black hole at the center of the Milky Way, is a cosmic powerhouse that has fascinated scientists and stargazers alike for decades. This colossal entity holds the key to understanding the dynamics of our galaxy and the fundamental laws that govern the universe. In this video, we'll dive deep into everything known about Sagittarius A, revealing its secrets and exploring the incredible phenomena surrounding this mysterious giant. For millennia, the center of the Milky Way was nothing more than a dense band of light arcing across the night sky. Ancient astronomers from civilizations long gone gazed upon it with awe, without understanding the incredible forces at play. The dusty bulge of stars, gas, and cosmic material near the core of our galaxy seemed impossibly far away and impenetrably hidden. But in the modern era, using the most powerful telescopes and space-based observatories ever built, scientists have pierced through this veil, and what they found was staggering. Anchoring the galaxy in place is an object millions of times more massive than our Sun, yet completely invisible, a supermassive black hole that we now call Sagittarius A. To begin to understand the importance and gravity, literally and figuratively, of Sagittarius A, we must first appreciate the nature of black holes themselves. A black hole is not an object in the traditional sense. It's a region of space where gravity has become so intense that nothing, not even light, can escape its pull. This point of no return, known as the event horizon, marks the boundary beyond which all information is lost to the universe. At its core lies a singularity, a point of infinite density where the known laws of physics break down completely. And yet, black holes are not cosmic vacuum cleaners randomly sucking up material. They are precise, gravitationally governed phenomena, born from the collapse of massive stars or the merging of dense celestial bodies over cosmic timescales. Sagittarius A, however, is not just any black hole. It's supermassive, millions of times the mass of our Sun, yet compressed into a space smaller than the orbit of Mercury. Its gravitational influence extends far beyond its invisible core, governing the motions of stars, gas clouds, and entire stellar populations within a vast sphere at the galaxy's center. In fact, it is Sagittarius A's immense pull that holds the Milky Way together, keeping billions of stars, including our own Sun, locked in their orbits like dancers in an unending celestial waltz. But how do we know this? After all, black holes by their very nature are invisible. They emit no light and swallow any signal that tries to escape. The discovery of Sagittarius A is one of the most remarkable detective stories in the history of astronomy. It began with subtle clues, strange radio emissions from the galactic core, observed first in the 1930s and 40s. Then came X-rays and infrared signatures that hinted at violent interactions happening in an otherwise dark region of space. But the real breakthrough came in the 1990s, when astronomers began tracking the orbits of stars near the center of the Milky Way using incredibly precise instruments like the Keck Observatory in Hawaii and later the Very Large Telescope in Chile. What they found was astonishing. Stars near the galactic center were moving at breakneck speeds, some hurtling around an invisible point at thousands of kilometers per second. The only possible explanation was a massive, compact object exerting a gravitational pull far greater than anything else nearby. Over years of observation, a clear picture began to emerge. At the center of all this stellar chaos was a single, dominant force, a supermassive black hole. And so, Sagittarius A was confirmed. In 2002, the motion of a particular star known as S2, which orbits incredibly close to the black hole, provided irrefutable evidence. Its path traced a perfect ellipse around a dark, motionless center, obeying the laws of gravity with uncanny precision. This wasn't just a theoretical construct anymore. This was real. And it was huge, about 4.3 million times the mass of the Sun. But this was just the beginning. Because Sagittarius A is not a static monument, it is a dynamic, living force at the heart of our galaxy. It feeds, occasionally, on the matter that drifts too close. It erupts with flares of X-rays and radio waves. It interacts with surrounding gas clouds and influences star formation. And most intriguingly, it holds secrets about the very structure and origin of the Milky Way. Let us take a moment to appreciate the environment near Sagittarius A. This is no quiet place. The galactic center is one of the most extreme environments in the known universe. Densely packed with stars, bombarded with radiation, and roiled with magnetic fields, it is a storm of matter and energy. Just within a few light years of Sagittarius A, you'll find stellar nurseries giving birth to massive stars, remnants of supernovae, and clouds of gas spiraling inward like water down a cosmic drain. And amid all this chaos, Sagittarius A sits at the center, silent, dark, and overwhelmingly powerful. Yet, perhaps the most mind-bending aspect of Sagittarius A is not just what it is, but what it represents. Black holes like this one are not mere anomalies. They are likely key to the formation of galaxies themselves. In fact, scientists believe that supermassive black holes and their host galaxies co-evolve. That is, the growth of the black hole and the development of the galaxy are intimately linked, possibly starting from the very birth of the universe. It's an astonishing idea, that the very structure of the Milky Way may owe its shape and stability to this invisible behemoth at its core. But what lies beyond the event horizon of Sagittarius A? What happens to the matter that crosses the threshold? These are questions that touch the edges of known physics. Theories abound, some suggesting a singularity, others proposing exotic objects like gravastars or even gateways to other universes. The truth is, we simply do not know. General relativity provides one set of answers, quantum mechanics another. Reconciling these views is one of the greatest unsolved problems in all of science. The study of Sagittarius A has also pushed the limits of technology. The Event Horizon Telescope, a global network of radio observatories acting as one Earth-sized telescope, made history in 2019 when it captured the first image of a black hole in another galaxy. In 2022, it turned its sights toward our own galactic center, producing the first image of the shadow of Sagittarius A, a glowing ring of light surrounding the darkness where the black hole hides. It was a triumph of collaboration and computational power, a visual echo of the space-time warping around an object we can never truly see. And yet, even with all our advances, Sagittarius A remains an enigma. Its quietness, compared to more active black holes that devour matter in luminous fits, puzzles scientists. Is it in a dormant phase? Has it consumed most of the available material near it? Or is it preparing for another burst of activity that could shake the heart of the galaxy? The truth is, this black hole is a paradox. It is the engine at the core of our galaxy, yet it emits no engine noise. It is the most massive object in our region of space, yet we cannot see it. It affects everything, yet it reveals almost nothing about itself. It is the ultimate cosmic mystery, the silent guardian, the invisible monster, the beating heart of the Milky Way. And we've only scratched the surface. Let us descend even deeper into the tale of Sagittarius A, because to truly appreciate the magnitude of what lurks at the center of our galaxy, one must immerse fully into not just the science, but the consequences, the mysteries, the theories, and the very fabric of space and time that warp and tremble in its presence. Imagine, for a moment, the scale of this cosmic leviathan. While its event horizon, the invisible boundary beyond which nothing returns, spans just over 12 million kilometers, its mass is equivalent to 4.3 million suns. That's 4.3 million stellar furnaces, each radiating light and energy, crushed by gravity into a region of space no larger than the orbit of Mercury. And yet, Sagittarius A does not shine. It does not announce its presence with fanfare. Instead, it broods in darkness, detectable only by the chaos it creates around it. When stars, gas clouds, or even wayward planets approach its vicinity, their paths become distorted, their velocities rise dramatically, and their fates become sealed by a gravitational grip that no force in the universe can overcome. The orbits of stars near Sagittarius A are among the most precise and astonishing measurements in all of modern astronomy. One of the most famous of these stars is S2. This star, roughly 15 times the mass of our Sun, orbits Sagittarius A in an elliptical path that takes just 16 years to complete, an extremely short orbital period when dealing with such vast celestial scales. As S2 swings close to the black hole, it accelerates to speeds exceeding 7,600 km per second, nearly 3% the speed of light. This is not just fast, it is physics in action at the very edge of our understanding. Such motion provides an extraordinary laboratory for testing Einstein's theory of general relativity, and indeed, S2's orbit has confirmed several predictions of this theory to remarkable precision. What makes Sagittarius A particularly fascinating is that it remains relatively dormant compared to other supermassive black holes observed in distant galaxies. Those black holes, often residing in the centers of quasars and active galactic nuclei, blaze with intense radiation, releasing tremendous amounts of energy as matter spirals into them in massive accretion disks. They emit jets of particles that span thousands of light years, lighting up the cosmos with their fury. Sagittarius A, by contrast, is surprisingly quiet. It emits occasional flares, short bursts of X-ray and infrared radiation, but for the most part, it slumbers. Why? There are several theories. One posits that Sagittarius A simply doesn't have a steady supply of material to feed on. In the vastness of space, despite being in a dense stellar region, matter can be scarce in the immediate vicinity of a black hole. Without fuel, even a beast of this magnitude cannot roar. Another possibility is that it has consumed most of the nearby gas and dust in the past and now enters periodic rest between brief meals. The flares we do see could be from small clumps of material, perhaps the remnants of disrupted stars or drifting gas clouds, that wander too close and are briefly devoured. In 2011, scientists observed such an encounter unfolding. A cloud of gas, dubbed G2, was on a collision course with Sagittarius A. Predictions ranged from fiery fireworks to total silence. As the cloud neared the black hole in 2014, all eyes were on the galactic center. Yet, surprisingly, nothing dramatic happened. G2 appeared to stretch, distort, and eventually pass by, but Sagittarius A barely reacted. This puzzling behavior deepened the mystery. Was G2 not a pure gas cloud, as initially thought? Could it have a hidden stellar core that prevented its complete destruction? These are the kinds of questions that keep astrophysicists awake at night. But perhaps even more intriguing than its feeding habits are the implications Sagittarius A has on our understanding of time, space, and the ultimate fate of information. According to general relativity, time itself slows down near the event horizon of a black hole. To a distant observer, objects falling into Sagittarius A would appear to move slower and slower, never quite crossing the boundary, fading away into redshifted obscurity. From the perspective of the falling object, however, time would proceed normally, until they reach the singularity, a place where the curvature of spacetime becomes infinite, and our understanding of physics breaks down entirely. This raises some of the most profound questions in theoretical physics. What happens to information that falls into a black hole? Quantum mechanics tells us that information cannot be destroyed. Yet black holes seem to erase all traces of the matter they consume, leaving behind only mass, charge, and spin. This contradiction is known as the black hole information paradox, and it has led to some of the most innovative and speculative theories in modern science. Could the information be encoded in the event horizon? Could black holes be holographic objects storing data on a two-dimensional surface? Or could there be wormholes or bridges to other universes through which the information escapes? Sagittarius A, by its very proximity and relative quiet, offers a unique opportunity to study these questions. It is the only supermassive black hole we can observe in such detail. Unlike distant quasars or galaxies billions of light-years away, Sagittarius A is just 26,000 light-years from Earth, close by galactic standards. This means we can observe it with a resolution impossible anywhere else. The Event Horizon Telescope's historic image of Sagittarius A in 2022 was more than just a technical triumph. It was a philosophical one, an unprecedented glimpse into the dark heart of our galaxy. But even this glimpse only scratches the surface. The physics of Sagittarius A challenges everything we think we know. Its presence bends space and time in ways that affect the orbits of stars, the flow of gas, and even the propagation of light itself. It serves as a laboratory not only for astrophysics but for cosmology, relativity, and quantum theory. What's even more fascinating is that Sagittarius A is not alone. Most, if not all, large galaxies are believed to harbor supermassive black holes at their centers. In fact, there seems to be a direct correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge. This relationship suggests that black holes and galaxies co-evolve, their destinies intertwined from the very beginning. Did Sagittarius A form first, attracting stars and gas that would become the Milky Way? Or did it grow from the remains of the early galaxy, fed by collapsing stars and merging clusters? The answer may lie in the early universe. After the Big Bang, matter began to coalesce under gravity into the first stars and galaxies. Somewhere in this primeval fog, the seeds of supermassive black holes were planted. Perhaps they formed from the direct collapse of massive gas clouds. Perhaps from runaway stellar mergers in dense clusters. However they formed, they quickly grew, becoming the anchors of cosmic structure. Sagittarius A is one such anchor, a survivor from a time long before the Earth, the Sun, or even the spiral arms of the Milky Way had taken shape. And it is still evolving. The galaxy moves, rotates, and shifts over cosmic time, and Sagittarius A moves with it, or more accurately, everything else moves around it. It is the ultimate center, the axis about which everything else turns. And yet, it is not static. The black hole could one day merge with another if the Milky Way collides with the Andromeda Galaxy, as is predicted to happen in about 4 billion years. When that happens, the two central black holes will spiral inward toward one another, releasing unimaginable energy in the form of gravitational waves before merging into an even larger supermassive black hole. This cosmic ballet, slow and majestic, would reshape the galactic structure entirely, and Sagittarius A would become something new. But until that distant day, Sagittarius A remains silent, powerful, unknowable. It is both a relic of the past and a harbinger of the future. It is a symbol of mystery, of gravity's ultimate triumph, of physics pushed to its limits. We can map its surroundings, track its stars, photograph its shadow, and model its interactions, but we cannot touch it, cannot probe beyond its veil. It is the ultimate riddle, a hole in space, filled with everything and nothing. As we continue this journey, we will unravel more layers of its complexity, from the relativistic jets it might someday produce, to the quantum mysteries lurking in its core, to the role it plays in regulating the life cycles of stars and galaxies. Because Sagittarius A is not just a black hole. It is a question. A question written in gravity and shadow, in silence and time, waiting for the universe to answer. And so, we continue into the fathomless depths of what Sagittarius A represents, not just as an astronomical object, but as a pivot around which entire disciplines of science revolve. To better understand Sagittarius A is to better understand the laws that govern the entire universe, and by extension, the origin and ultimate destiny of everything that exists within it. One of the most powerful ways in which Sagittarius A has transformed modern astronomy is through the development and refinement of observational technology. Detecting something that emits no light is not a trivial task. For much of the 20th century, black holes were purely theoretical entities, predicted by Einstein's equations but lacking direct observational evidence. Sagittarius A changed all of that. It became the primary testing ground, a target so close that its influence on nearby stars and gas clouds could be measured in real time, providing proof of its existence far beyond any reasonable doubt. The importance of infrared and radio astronomy cannot be overstated when it comes to observing Sagittarius A. The center of our galaxy is obscured by thick clouds of interstellar dust that block visible light. Traditional telescopes are essentially blind in that direction. But longer wavelengths, such as those of infrared and radio waves, can penetrate the dust and reach our instruments. That's why some of the most advanced observatories, including the Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Event Horizon Telescope, a global network of radio dishes, are so crucial in this field. They allow us to peer directly into the galactic core. And what do we see when we peer through this cosmic fog? We see stars being flung around a seemingly empty patch of space with astonishing speed and precision. We see gas clouds spiraling inwards, occasionally flaring in bursts of radiation as they are heated by tidal forces and friction. We see magnetic fields twisting into chaotic patterns near the event horizon. We even see changes in the polarization of light, which tells us about the warped structure of spacetime near the black hole. Every photon we capture is a clue. Every fluctuation in brightness, every shift in frequency, every unexpected motion, it all adds to the growing mosaic of understanding that surrounds this enigmatic void. But beyond the observations, beyond the data, there are the theories. And when it comes to Sagittarius A, theories run the gamut from the firmly established to the wildly speculative. One of the most compelling frameworks we use to understand black holes is general relativity, Einstein's magnum opus. According to relativity, gravity is not a force in the traditional sense, but a curvature of spacetime caused by mass and energy. The more massive an object, the more it warps the spacetime around it. A black hole is simply a region where this curvature becomes so extreme that not even light can escape. It is a one-way membrane, an object whose surface, the event horizon, represents the point of no return. But Einstein's theory, elegant and powerful as it is, cannot tell us what happens inside a black hole. It breaks down at the singularity, a theoretical point of infinite density and zero volume at the black hole's core. Here, spacetime curves infinitely, and the laws of physics as we know them cease to apply. This is where quantum mechanics must step in. But combining quantum theory with general relativity has proven to be one of the greatest unsolved problems in modern science. Many physicists believe that a theory of quantum gravity, such as string theory or loop quantum gravity, is necessary to fully understand what lies within Sagittarius A. Such a theory would reconcile the probabilistic nature of quantum mechanics with the smooth, continuous spacetime of relativity. It might reveal that the singularity is not a true point, but a structure of finite size where quantum effects prevent the collapse into infinite density. It might even suggest that black holes are not entirely black, that they radiate tiny amounts of energy, as proposed by Stephen Hawking, in the form of Hawking radiation. If Hawking radiation does exist, then Sagittarius A, despite its colossal mass, would slowly evaporate over unimaginable timescales, trillions upon trillions of years. This process would eventually cause the black hole to shrink and vanish, leaving behind a faint wisp of radiation and perhaps the information it once devoured. But this raises new questions. Where does the information go? Is it lost forever? Is it preserved in some hidden dimension? Is it encoded on the surface of the event horizon, as the holographic principle suggests? The holographic principle is one of the most intriguing ideas to emerge from black hole physics. It suggests that all the information contained within a volume of space can be described by data encoded on its boundary. In the case of Sagittarius A, this would mean that everything it has ever consumed, stars, gas, light, possibly even planets, still exists in some form, not inside the black hole, but on its surface, like a cosmic data archive. If true, this would revolutionize our understanding of space, time, and reality itself. The universe, in essence, could be a hologram, a three-dimensional projection of information stored on two-dimensional surfaces. But let us not lose ourselves entirely in theory. The real, observable effects of Sagittarius A are equally astonishing. The gravitational field near the black hole is so intense that it affects not just nearby stars, but the overall structure of the galaxy. It acts as a stabilizing anchor, maintaining the coherence of the Milky Way's spiral arms. It also influences the flow of interstellar gas, the birth and death of stars, and the evolution of stellar populations in the galactic bulge. The black hole's environment is also rich with exotic phenomena. There are mysterious radio bubbles, giant lobes of energetic particles extending above and below the galactic plane, that may have originated from past eruptions of Sagittarius A. These structures, discovered through sensitive X-ray and radio observations, hint at a more violent past. Was Sagittarius A once an active galactic nucleus, devouring matter at a furious pace and spewing out jets of energy? If so, it may become active again in the future. The galaxy breathes, and Sagittarius A may exhale once more. Then there are the mysterious objects known as G-objects, star-like entities near Sagittarius A that behave strangely. They appear to be gas clouds but don't dissipate as expected. Some scientists believe they may be stars shrouded in thick envelopes of dust and gas, possibly the result of stellar collisions or mergers. These objects challenge our understanding of what can survive near a black hole, and what happens to matter under such extreme conditions. The region around Sagittarius A is also one of the most dynamic and volatile areas in the galaxy. It contains a high density of massive stars, young and old, as well as clusters, pulsars, neutron stars, and possibly other black holes. These objects interact gravitationally, magnetically, and radiatively, creating a chaotic but fascinating environment. Observing these interactions provides insights into the behavior of matter under conditions that cannot be replicated on Earth: temperatures of millions of degrees, magnetic fields trillions of times stronger than our own, and densities that defy comprehension. As we build ever more powerful instruments, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, our view of Sagittarius A will become even clearer. We will be able to resolve finer details, detect subtler effects, and perhaps even watch new matter fall into the black hole in real time. We will refine our models, test our theories, and challenge our assumptions. Every new observation is another piece of the puzzle, a step closer to understanding not just Sagittarius A, but the nature of reality itself. And all the while, Sagittarius A remains indifferent. It does not care that we study it, fear it, or mythologize it. It exists beyond human emotion, beyond time, beyond light. It is a reminder of the vastness of the cosmos and the limits of human comprehension. Yet, in studying it, we push those limits ever outward. We venture into the unknown, armed with curiosity and driven by wonder. This is only the beginning. Much more lies ahead. As we delve even deeper into the enigma that is Sagittarius A, the very concept of a black hole continues to evolve, stretching our understanding of both astrophysics and the fundamental fabric of the cosmos. To truly appreciate the gravity, quite literally, of Sagittarius A's existence, one must consider the journey of how humanity even came to realize such a force could exist, buried at the heart of our galaxy, unseen but omnipresent in its influence. Long before the term black hole entered the scientific lexicon, philosophers and mathematicians pondered the notion of a body so massive and dense that even light could not escape it. The earliest hints came in the 18th century, when Jean Michel and Pierre-Simon Laplace theorized about dark stars that might trap light due to extreme gravitational pull. But it wasn't until Albert Einstein introduced the general theory of relativity in 1915 that the modern concept of a black hole began to crystallize. Einstein's equations predicted that if a massive object were to collapse under its own gravity beyond a certain limit, it would create a point in space where gravity becomes infinite, a singularity. But Einstein himself doubted the physical reality of such objects. The equations, however, did not lie. Over time, solutions to the Einstein field equations, most notably the Schwarzschild solution, mathematically described what we now understand as a black hole. Fast forward to the modern era. Astronomers began noticing peculiar movements of stars in the central region of the Milky Way, stars orbiting an invisible, compact object at extraordinary speeds. These observations culminated in a groundbreaking discovery: a supermassive object, dark and massive, exerting gravitational dominance over its neighborhood. This object, Sagittarius A, was eventually identified as a black hole with a mass of approximately 4 million times that of our Sun. But how does one weigh an invisible giant? The answer lies in observing its gravitational dance partners. Stars such as S2, which orbits Sagittarius A, have provided crucial data. This star, in particular, completes an orbit roughly every 16 years and comes incredibly close to the black hole, a mere 17 light-hours away at its closest approach. That's about 4 times the distance from the Sun to Pluto. During this passage, S2 reaches speeds exceeding 7,000 kilometers per second, a staggering velocity that can only be explained by the presence of a supermassive object. The meticulous tracking of S2 and other stars was accomplished through high-precision infrared imaging using adaptive optics, a technique that corrects for the distortions caused by Earth's atmosphere. Instruments such as gravity, part of the European Southern Observatory's Very Large Telescope Interferometer, have allowed astronomers to observe the motion of these stars with unprecedented accuracy. These observations have not only confirmed the mass and location of Sagittarius A but have also provided experimental confirmation of general relativity in extreme gravitational fields. In 2022, a new milestone was reached. The Event Horizon Telescope collaboration released the first-ever image of Sagittarius A's shadow. This was no ordinary photograph. It was the culmination of a global effort involving radio telescopes spread across the Earth, from the South Pole to Spain, from Hawaii to Chile, all synchronized to act as a single, Earth-sized virtual telescope. The image, a glowing ring of light surrounding a dark central region, matched theoretical predictions and served as direct visual evidence of a supermassive black hole at the center of our galaxy. But what does this glowing ring represent? It's not the black hole itself, that remains invisible. Instead, it is the photon ring, a region where light orbits the black hole due to the extreme curvature of spacetime. Photons can loop around the black hole multiple times before either escaping or plunging in. The light we see comes from hot gas and dust being accelerated and heated to immense temperatures as it spirals into the event horizon, emitting radiation in the process. This process forms what we call the accretion disk, a bright, turbulent structure that encircles the black hole. This accretion disk, though often only faintly active in Sagittarius A, is the key to unlocking its secrets. At times, the black hole experiences what are called flaring events, sudden bursts of infrared and X-ray emissions thought to be caused by the infall of clumps of matter or magnetic reconnection events within the accretion flow. These flares, which occur on timescales of minutes to hours, give astronomers a chance to observe Sagittarius A's behavior in near real time, offering clues about the physics of matter under extreme gravitational stress. The behavior of matter near Sagittarius A also leads us into one of the most mysterious aspects of black holes, the no-hair theorem. This principle states that all black holes can be completely described by just three external parameters: mass, charge, and angular momentum. They are, in essence, the ultimate simplifiers of matter. All the complex information about the particles, atoms, and objects that fall into them is supposedly lost, leaving behind only these three characteristics. This idea, while elegant, raises profound questions about the nature of information and whether it is truly lost or preserved in some hidden form, a conundrum famously known as the black hole information paradox. Some physicists believe that resolving this paradox could be the key to a theory of everything, a unified framework that reconciles gravity with quantum mechanics. Others suggest that black holes might be gateways to other universes, wormholes, or even repositories of alternate realities encoded in quantum fluctuations at the event horizon. While these ideas remain speculative, they are grounded in real mathematical models and are being explored by serious theorists. Sagittarius A, being our nearest supermassive black hole, serves as the ultimate laboratory for testing such ideas. Unlike the monstrous black holes at the centers of other galaxies, which are often obscured or too distant for detailed observation, Sagittarius A offers a front-row seat to one of the universe's most extreme environments. By studying it, we gain not only knowledge of black holes themselves but also insights into the early formation and evolution of galaxies. Indeed, the relationship between black holes and galaxies appears to be a symbiotic one. Observations have shown that the mass of a galaxy's central black hole correlates with the mass of the galaxy's bulge, a relationship known as the M-sigma relation. This suggests that black holes play a crucial role in shaping their host galaxies, regulating star formation through feedback processes, and possibly even influencing galactic morphology. Sagittarius A may currently be in a relatively quiescent state, but evidence suggests that it has not always been so. In the past, it may have consumed vast amounts of matter, releasing powerful jets and winds in the process. These outbursts could have heated surrounding gas, suppressed star formation, and altered the chemical composition of the galactic center. The scars of this activity may still be visible in features such as the Fermi bubbles, massive structures extending above and below the plane of the Milky Way, likely formed by energetic events linked to the black hole. What lies ahead for Sagittarius A? Predicting the future of a black hole is no easy task, but astronomers are watching closely. One particular event that drew international attention was the approach of a mysterious gas cloud known as G2 in 2013. Many expected a dramatic increase in activity as the cloud neared the black hole, but Sagittarius A remained largely undisturbed. This led to revised models of G2's structure. Perhaps it was not a gas cloud at all, but a star enveloped in dust, or the remnant of a stellar merger. Regardless, the event provided valuable data and demonstrated just how complex and unpredictable the galactic center truly is. As we build more sensitive telescopes and develop more sophisticated models, our understanding of Sagittarius A will continue to deepen. New observatories, such as the Square Kilometre Array and next-generation X-ray telescopes, will allow us to detect fainter signals and probe smaller scales. The dream of mapping the spacetime near the event horizon in exquisite detail, to see matter twisting and stretching under the influence of relativistic gravity, is within reach. Yet, for all that we've learned, Sagittarius A remains a profound mystery. It is a place where time slows to a crawl, where light is trapped, where space itself folds in upon itself. It is the end of everything we know, and possibly the beginning of something we have yet to imagine. And as we stand on the threshold of this abyss, peering in with minds sharpened by science and hearts stirred by wonder, we find ourselves asking not just what lies at the center of the galaxy, but what lies at the center of reality itself. From the abyss of Sagittarius A, our attention turns to the very architecture of space and time that it disrupts. Black holes, and Sagittarius A in particular, are not just massive objects pulling in matter, they are distorters of space-time, altering the fundamental geometry of the universe around them. This distortion is not hypothetical, it's measurable, observable, and has real consequences on the movement of stars, the warping of light, and the behavior of time itself. Near Sagittarius A, time doesn't pass the way it does for us on Earth. According to Einstein's general relativity, time slows down in strong gravitational fields, a phenomenon known as gravitational time dilation. For a hypothetical astronaut orbiting just outside the event horizon of Sagittarius A, time would slow to a crawl compared to observers on Earth. This means that while only a few minutes might pass for someone near the black hole, years or even centuries could pass for the rest of the galaxy. This concept, once thought to be purely theoretical, has been demonstrated through precise measurements of time discrepancies between Earth-bound and orbiting satellites, and it plays a significant role in modern GPS systems. This time-warping effect is one of many reasons black holes have fascinated physicists and science fiction writers alike. The event horizon, the boundary beyond which nothing, not even light, can escape, represents a one-way threshold into this warped region. It is the ultimate veil, concealing whatever lies within from our universe forever. For Sagittarius A, the event horizon spans about 24 million kilometers across, about 17 times wider than the Sun, yet its mass remains packed into this incredibly compact region. This compression of matter into an infinitesimal point, the singularity, is where our current understanding of physics breaks down. The singularity is the heart of the black hole, a place of infinite density where space and time cease to behave normally. But what actually occurs at the singularity remains unknown. Our equations fail, unable to reconcile the infinite curvature of spacetime predicted by general relativity with the probabilistic nature of quantum mechanics. This is where the need for a theory of quantum gravity becomes urgent, a theory that could merge general relativity with quantum physics into a single framework. Numerous candidates have been proposed, including string theory and loop quantum gravity. Some of these theories suggest that singularities might not be true infinities but regions of extreme density where quantum effects become dominant, possibly even bouncing back into new universes, a concept echoed in the theory of black hole cosmology. In this view, every black hole could potentially spawn a new universe, making Sagittarius A not just a dead end but a gateway to something beyond. Back in observable territory, Sagittarius A's influence extends far beyond its immediate surroundings. The gravitational pull it exerts shapes the orbits of stars over thousands of light years, anchoring the Milky Way's spiral arms in their majestic rotation. Without such a massive object at the center, our galaxy's structure might not be stable over cosmic timescales. The central black hole acts like a keystone, holding the entire galactic architecture together. Interestingly, Sagittarius A is relatively quiet compared to the raging quasars found in distant galaxies. Quasars are powered by supermassive black holes that are actively consuming vast quantities of matter, emitting torrents of radiation that can outshine the rest of their galaxy combined. Sagittarius A, by contrast, consumes matter at a much slower rate, a behavior known as being underfed or low luminosity. Despite this quiet demeanor, Sagittarius A does occasionally emit bursts of X-rays and infrared light, indicating that it is still active, albeit modestly. This subdued activity provides scientists with a rare opportunity. In more violent galaxies, the intense radiation and energetic outflows from central black holes obscure the surrounding region. But in our galaxy, the relative calm of Sagittarius A allows astronomers to observe the central stars and gas with extraordinary clarity. This window into the galactic core has yielded insights into star formation under extreme conditions, the dynamics of dense star clusters, and the complex interplay between black holes and their host galaxies. The environment around Sagittarius A is teeming with phenomena that push the boundaries of known physics. One such feature is the presence of magnetized plasma spiraling inward toward the event horizon. This plasma, heated to millions of degrees, emits radiation across the electromagnetic spectrum, from radio waves to X-rays. The motion of this plasma is governed not just by gravity but also by intense magnetic fields that twist and tangle, potentially triggering flares and jets. These magnetic fields play a crucial role in the black hole's feeding process. They can create turbulence in the accretion disk, funnel matter inward, and even launch particles away at near-light speeds in narrow beams known as relativistic jets. Although Sagittarius A does not currently exhibit large-scale jets like some other active galactic nuclei, signs of past activity suggest that it may have once emitted such jets, influencing the interstellar medium across the galaxy. Observations of these interactions are supplemented by detailed computer simulations, virtual laboratories where scientists can explore the behavior of matter and light under conditions too extreme to replicate on Earth. These simulations incorporate general relativity, magnetohydrodynamics, and radiation physics to create models that can be compared with actual observations. The close match between simulation and data in the case of the Event Horizon Telescope image of Sagittarius A is a testament to how far this field has come. Still, even the most detailed simulations must grapple with uncertainties. For instance, the spin of Sagittarius A remains elusive. Black holes can spin, and this spin affects everything from the shape of the event horizon to the dynamics of the accretion disk. A spinning black hole drags spacetime around with it, a phenomenon known as frame dragging or the lens stirring effect. Detecting this spin requires precision measurements that push our instruments to their limits, but doing so could unlock further secrets about the black hole's formation history and growth. How did Sagittarius A become so massive? There are several theories. One possibility is that it formed from the merger of several smaller black holes, remnants of massive stars that died early in the galaxy's life. Another idea suggests that it grew through the accretion of gas and stars over billions of years. Yet another proposes the direct collapse of an enormous gas cloud in the early universe, bypassing the stellar stage altogether. Each scenario has different implications for our understanding of cosmic evolution, and determining which one is correct remains a major challenge. Despite its many mysteries, Sagittarius A offers more than scientific intrigue. It also provides a profound philosophical reflection on the nature of existence. Black holes, by their very nature, challenge our understanding of space, time, causality, and reality. They force us to confront questions about the beginning and end of the universe, the limits of knowledge, and the fate of information. In a sense, Sagittarius A is a mirror, not a physical one, but a cosmic one, reflecting the depths of our curiosity and the limits of our comprehension. It stands as both an endpoint and a point of origin, a paradox that sits calmly at the center of the galaxy while stars whirl around it in dizzying orbits, oblivious to the profound mysteries just beyond the veil. As we continue to study it, Sagittarius A draws us closer to answering some of the biggest questions in science. What happens at the singularity? Is information truly lost in a black hole, or does it live on in some hidden form? Can we unify gravity and quantum mechanics into a single, elegant theory? Will the study of black holes reveal the true nature of time, or even show us how to transcend it? These are the questions that Sagittarius A poses, not with words, but with the silent gravity of its presence, the distortions of its space, and the whispers of light swirling around its edge. And so we continue, watching, listening, and imagining, knowing that the journey into the heart of darkness is also a journey into the light of understanding. As we push further into the mysteries surrounding Sagittarius A, we must not overlook the powerful role this object plays in shaping the very identity of our galaxy. Located about 26,500 light-years from Earth in the direction of the constellation Sagittarius, this black hole is not merely a background player. It is the gravitational anchor of the Milky Way, the unseen conductor orchestrating the cosmic ballet of hundreds of billions of stars. Its location, deep within the galactic bulge, makes it difficult to observe in visible light. Intervening dust and gas between Earth and the galactic center obscure our direct view. But humanity has never been one to back away from a challenge. By using radio waves, which can penetrate these cosmic obstacles, astronomers have managed to peer through the murk. Instruments like the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have been instrumental in mapping the activity around Sagittarius A with unprecedented resolution. The environment around this supermassive black hole is one of the most extreme in the universe. Temperatures soar into the millions of degrees, particles race around at nearly the speed of light, and radiation floods every crevice of space. Yet even within this chaos, there exists a strange kind of order. Stars follow predictable orbits. Gases spiral inward in structured accretion disks. Magnetic fields loop and twist, often in complex but not random patterns. Among the most compelling of these stellar dancers are the so-called S-stars. These are a group of stars locked in tight, fast orbits around Sagittarius A. One of the most famous of these is S2, a star that completes an orbit around the black hole in just 16 years, an astonishing speed given the immense distances involved. When S2 approaches its closest point to the black hole, it travels at about 3% the speed of light and experiences extreme gravitational redshift, a stretching of its light toward longer wavelengths due to the intense gravity. The motion of stars like S2 provides irrefutable proof that an object of immense mass resides at the center of our galaxy. The orbital data allows astronomers to calculate this mass with precision, around 4.3 million times that of our Sun, confined within a region no larger than our solar system. Such density leaves no room for doubt. This can only be a black hole. But beyond its mass and gravitational pull, Sagittarius A also acts as a cosmic engine, subtly influencing the behavior of the interstellar medium across the Milky Way. Winds and outflows from the center can push gas and dust into distant regions, potentially triggering new waves of star formation or stifling it altogether. Some astrophysicists believe that periodic outbursts from the black hole could have rippled through the galaxy in the past, leaving behind faint but measurable traces, cosmic echoes of ancient activity. One such piece of evidence is the Fermi bubbles, massive, balloon-like structures that extend tens of thousands of light-years above and below the galactic plane. Detected by the Fermi Gamma Ray Space Telescope, these bubbles emit high-energy radiation that suggests a cataclysmic event occurred in the galactic core millions of years ago. Many scientists theorize that an energetic outburst from Sagittarius A is responsible for their creation, possibly during a time when the black hole consumed a large amount of matter and briefly became a quasar-like beacon of activity. This possibility raises fascinating questions. Could Sagittarius A flare up again in the future? What would trigger such an event? And how would it affect life on Earth? The answers depend on the black hole's feeding habits. Sagittarius A is currently underfed by galactic standards, but this could change. The galactic center is a turbulent place, with clouds of gas, rogue stars, and other debris constantly drifting through. If a sufficiently large object were to fall into Sagittarius A, it could reignite the black hole's appetite, causing it to emit jets and radiation that might alter conditions across the galaxy. Indeed, we've seen hints of such events even in modern times. In 2019, astronomers observed a sudden and unexpected brightening near Sagittarius A. The infrared flare, though short-lived, was the brightest ever recorded from this object, suggesting that something unusual had happened, perhaps a clump of matter falling into the event horizon. Though this wasn't a catastrophic event, it served as a reminder that the black hole is not entirely dormant. Understanding these behaviors requires more than observation. It demands theory, simulation, and continuous refinement of models. The gravitational forces near a black hole like Sagittarius A are so intense that traditional Newtonian physics is inadequate. Instead, researchers rely on the framework of general relativity, augmented by computational models that take into account magnetic fields, quantum effects, and relativistic motion. These models are constantly tested against new data. The Event Horizon Telescope collaboration, for example, is not content with merely imaging black holes. They aim to turn black holes into laboratories for testing the laws of physics. By analyzing the light that escapes from the edges of the event horizon, known as the photon ring, scientists hope to uncover subtle deviations that could point to new physics, such as the existence of extra dimensions or the validity of alternative theories of gravity. The photon ring itself is a fascinating construct. Light that grazes the event horizon can circle the black hole multiple times before escaping. This creates a series of nested rings, each representing a photon that made a different number of orbits before breaking free. Theoretically, these rings encode a vast amount of information about the black hole's spin, mass, and structure, and may even hold clues to resolving the black hole information paradox, the puzzle of whether information that falls into a black hole is truly lost forever. This paradox, first articulated by Stephen Hawking, strikes at the core of physics. According to quantum mechanics, information cannot be destroyed. Yet black holes seem to do just that. The resolution of this paradox remains one of the greatest unsolved problems in science. Some theorists believe that information is somehow encoded in the event horizon itself, possibly through a mechanism called holography, where the three-dimensional data is stored on a two-dimensional surface. Others propose more radical ideas, such as black hole complementarity or the firewall hypothesis. Whatever the answer, Sagittarius A offers the best opportunity to explore these ideas empirically. It is close enough to observe with great detail, quiet enough to provide a stable testing ground, and mysterious enough to keep us guessing. In this way, Sagittarius A is not just a distant phenomenon, it is a cosmic crucible in which the laws of nature are tested to their limits. Every particle that orbits it, every flare it emits, every wave of radiation it sends through the galaxy carries with it a piece of the puzzle. And as our instruments grow more precise and our theories more sophisticated, we inch closer to understanding what lies behind the event horizon. And yet, despite all we know, Sagittarius A retains an almost mystical quality. It is a place where time slows to a stop, where light is trapped in eternal orbits, where the very fabric of reality is torn and stretched. It is a region we can never visit, never probe directly, never see inside, yet one that shapes our galaxy in profound and fundamental ways. It is a silent titan, a cosmic heart that beats slowly and invisibly, pumping gravity instead of blood, shaping the Milky Way not with sound but with influence. And like all hearts, it holds secrets we are only just beginning to understand. Its silence, paradoxically, speaks volumes. While Sagittarius A emits occasional flares and bursts, its most profound influence lies in the gravitational dominion it exercises. Every orbit of every star in the Milky Way, ours included, is ultimately dictated by the presence of this invisible monolith. The spiral arms of our galaxy, the clustering of stars near the center, even the long-term stability of galactic structures all trace back, in part, to the enormous mass housed within Sagittarius A. In fact, this is a critical reason why astronomers believe most, if not all, galaxies harbor a supermassive black hole at their core. Observations of galaxies from the elliptical giants to irregular dwarfs reveal a startling regularity. Their central black holes seem to scale proportionally with the size and mass of the surrounding bulge. This galactic black hole connection, sometimes referred to as the M-sigma relation, hints at a coevolutionary process. In essence, as galaxies grow and merge, so do their black holes, feeding off each other in a cosmic feedback loop spanning billions of years. What's particularly fascinating about Sagittarius A is its relative quiescence. Compared to the ferocious cores of active galactic nuclei, such as quasars, blazars, or Seyfert galaxies, our Milky Way's center is, by comparison, docile. There are no titanic jets of plasma stretching across intergalactic space, no glaring X-ray beacons announcing its presence to distant observers. It hums rather than roars. But why? The answer likely lies in its current lack of fuel. Like a dormant volcano, Sagittarius A isn't inactive because it can't erupt, it's simply not being fed. The material in its immediate vicinity is either too diffuse, too hot, or moving too fast to be captured. Every now and then, a star may stray too close, or a gas cloud might begin to spiral inward, but large-scale, consistent accretion is currently not happening. In the cosmic scheme of things, this makes Sagittarius a quiet neighbor, but also a profoundly mysterious one. Yet, even in its slumber, the black hole's presence allows us to probe the very nature of space-time. Einstein's general theory of relativity makes several key predictions about the environment near such a massive object. Predictions that can now be tested thanks to increasingly precise measurements. One of the most significant of these tests involved the orbit of the star S2. As it swung by the black hole in 2018, astronomers detected a tiny but crucial deviation from its expected path. The light from the star was redshifted exactly as predicted by general relativity. This moment marked a major confirmation of Einstein's ideas, not in a laboratory, but in the depths of the galaxy. There is something almost poetic in this, a star's light, distorted by gravity, whispering secrets to scientists light years away. The very fabric of space bends in the presence of mass, and Sagittarius A, with its immense bulk, warps the Milky Way like a marble sitting on a trampoline. It is this warping that governs not just orbits and motion, but the flow of time itself. Near the event horizon, time slows dramatically compared to regions further away. A hypothetical observer orbiting close to Sagittarius A would experience time at a significantly slower rate than someone on Earth. This time dilation effect is more than a theoretical curiosity, it is a measurable, observable aspect of reality. And this leads us deeper into the black hole's paradoxes. For an outside observer, nothing can ever truly fall into a black hole. Instead, objects appear to freeze and fade at the event horizon. But for the object itself, time continues unabated, and it crosses the event horizon in finite time. This divergence between perspectives, between what is seen and what is experienced, highlights the extreme warping of space and time in this environment. It challenges our intuitions, our definitions of reality, and forces us to confront the limits of our understanding. Meanwhile, the question of what lies beyond the event horizon remains one of the greatest mysteries in physics. The singularity at the center of Sagittarius A, a point of infinite density where our current laws of physics break down, is not something we can observe directly. It is hidden, cloaked in absolute darkness. But theoretical physics offers several intriguing possibilities. One idea is that the singularity is not a point but a bridge, a hypothetical wormhole that connects to another region of space or time. Though largely speculative, this concept has captivated scientists and science fiction writers alike. Another possibility, suggested by certain interpretations of quantum gravity, is that the core of a black hole may be replaced by a Planck star, a dense object where quantum pressure halts complete collapse. These ideas, though exotic, are part of serious scientific discourse, because when it comes to black holes, conventional thinking often fails. Sagittarius A also forces us to consider information. In classical physics, anything that falls into a black hole is gone forever. But quantum theory says information cannot be destroyed. This creates a tension between two foundational pillars of modern science. Some proposed resolutions suggest that information is preserved in subtle patterns of Hawking radiation, while others posit the holographic principle, that all the information about a three-dimensional object can be encoded on a two-dimensional surface, like the event horizon. If true, this would mean that Sagittarius A is not just a hole in space, but a repository of cosmic data, a dark archive containing the history of everything it has consumed. As we reflect on the nature of this entity, we are reminded that black holes are not merely dead ends. They are regions of intense transformation. They compress matter and information, challenge the continuity of spacetime, and provide natural laboratories for exploring the deepest laws of the universe. In a sense, Sagittarius A is not an anomaly but a focal point, a lens through which the universe examines itself. And our observations are only just beginning. With next-generation telescopes like the James Webb Space Telescope, and future enhancements to the Event Horizon Telescope Array, we are poised to gather even more detailed data. These instruments will allow us to peer deeper into the galactic center, to observe fainter stars, trace finer details in accretion flows, and perhaps even detect the shadow of the event horizon with greater clarity. Each new discovery will add another brushstroke to the cosmic portrait we are painting. We are also exploring the possibility of gravitational waves, ripples in space-time caused by massive accelerating objects. While most current detections come from mergers of smaller black holes or neutron stars, future observatories like LISA, the Laser Interferometer Space Antenna, could detect low-frequency waves from events involving supermassive black holes. If Sagittarius A were ever to merge with another giant, say, from a colliding dwarf galaxy, we could witness such a cataclysmic event not with light, but with the very fabric of space ringing like a bell. All of this brings us to a larger truth. The story of Sagittarius A is also the story of us. The atoms in our bodies, the stars we see in the night sky, the very shape of our galaxy, all of these are intertwined with the existence of this unseen giant. It is a reminder of how small we are, but also how capable we are. With nothing but ingenuity, mathematics, and increasingly sophisticated instruments, we have uncovered the presence of something utterly alien, hidden behind thousands of light years of dust and gas. And yet, for all its remoteness, Sagittarius A is intimately connected to the fate of our galaxy. As the Milky Way continues its slow-motion collision with the Andromeda Galaxy, an event that will unfold over the next several billion years, the two central black holes will eventually spiral into each other, releasing vast amounts of energy and reshaping the new galaxy that emerges. When that happens, Sagittarius A will merge with Andromeda's black hole, forming a supermassive entity far larger than either. It's awe-inspiring to consider. The quiet black hole at our galaxy's center is not a relic. It is a participant in an ongoing story, a cosmic narrative that spans from the birth of stars to the merging of galaxies. And we, tiny and fleeting as we are, have the privilege of witnessing and understanding it. The vastness of Sagittarius A's influence extends beyond mere gravity and mass. It shapes the very architecture of the Milky Way in subtle yet profound ways. At the galactic center, where stars crowd in far greater numbers than in the spiral arms, the gravitational pull of Sagittarius A orchestrates an intricate celestial dance. The so-called nuclear star cluster surrounding the black hole is a bustling hive of activity, with stars whipping around at breakneck speeds in orbits that can be completed in mere years. Cosmic blink of an eye compared to the Sun's 225 million-year galactic orbit. These orbits offer astronomers invaluable clues about the black hole's properties. By meticulously tracking stellar paths with infrared telescopes, since visible light cannot penetrate the dense dust, the mass of Sagittarius A has been measured with extraordinary precision. It's roughly 4 million times that of our Sun, compressed into a volume no larger than our solar system. This incredible density leaves no doubt. This object is a supermassive black hole. But there's more to the environment around Sagittarius A than just stars and gravity. Surrounding it is a swirling sea of gas and dust, remnants of stars long since torn apart by tidal forces or expelled in violent stellar winds. These clouds, some moving at thousands of kilometers per second, are occasionally drawn inwards, spiraling ever closer to the event horizon. As matter accelerates and compresses, it heats up, emitting X-rays and other forms of radiation that telescopes can detect. This glow, though faint compared to active galactic nuclei, provides another window into the feeding habits of our black hole. Occasionally, larger objects, such as rogue stars, stellar remnants, or dense molecular clouds, venture too close, crossing the tidal radius. The immense gravitational gradient tears them apart in a cataclysmic process known as a tidal disruption event. Such episodes, though rare, can cause bright flares detectable across multiple wavelengths. While Sagittarius A is relatively calm now, past records and simulations suggest it has experienced periods of more intense activity, perhaps billions of years ago, when the Milky Way was more dynamic. One fascinating recent discovery involves the so-called G objects. These are mysterious compact sources that behave like both stars and gas clouds. They seem to survive perilously close to the black hole without being completely shredded. Their nature is still debated, but they may represent young stars enshrouded in thick gas or remnants of stellar mergers. Studying these objects challenges our understanding of how matter behaves under extreme tidal forces. Beyond these immediate surroundings, Sagittarius A has shaped the galactic bulge itself. This central region is a dense, spheroidal congregation of stars, older and redder than those in the spiral arms. The black hole's gravitational grip helps maintain this structure, preventing it from dispersing and influencing star formation rates. It also affects the orbits of globular clusters, massive groups of ancient stars orbiting the galaxy. In essence, Sagittarius A's presence is the gravitational anchor of the Milky Way's core. From a cosmological perspective, Sagittarius A offers insights into the formation and evolution of galaxies throughout the universe. By comparing our galactic center to more active or more massive black holes, scientists piece together the life cycles of these enormous objects. Our black hole, sitting in a relatively quiet galaxy, contrasts with quasars, black holes billions of times more massive that blaze with the light of infalling matter. These comparisons help build models explaining how black holes grow through accretion and mergers, and how their energetic output shapes the galaxies around them. Despite the progress, many puzzles remain. One is the exact mechanism of accretion in Sagittarius A. Unlike luminous quasars, Sagittarius A accretes at an extremely low rate, leading to the classification of a radiatively inefficient accretion flow. This means that most of the infalling matter doesn't convert its gravitational energy into light efficiently, making the black hole faint despite its mass. Understanding the physics behind this inefficiency requires complex plasma simulations, magnetohydrodynamics, and comparisons with observations. Additionally, the spins of supermassive black holes like Sagittarius A are difficult to measure but crucial for understanding their history. A rapidly spinning black hole suggests growth through prolonged accretion, while slower spins might indicate mergers with other black holes. Recent studies use the shape of the innermost accretion flow, jet properties, and relativistic effects to estimate spin, but definitive answers remain elusive. Sagittarius A also connects to the quest for quantum gravity. Black holes are the ultimate testing grounds for theories uniting quantum mechanics and general relativity. The event horizon and singularity represent conditions where both frameworks must be reconciled. Hypotheses like the firewall paradox and black hole complementarity arise from this tension, pushing physicists to rethink foundational principles. In a more philosophical vein, the existence of Sagittarius A invites us to consider the limits of knowledge. Black holes, by their nature, guard secrets behind horizons no light escapes from. This boundary challenges our notions of causality, determinism, and the nature of reality itself. It forces scientists to explore ideas like holography and the multiverse, where information and space-time behave in unexpected ways. Looking forward, missions like the gravity instrument on the Very Large Telescope Interferometer are sharpening our view, resolving details within microarcseconds, equivalent to discerning a coin on the Moon from Earth. These observations continue to test Einstein's theory and reveal the dynamic environment near Sagittarius A. The black hole also plays a role in the future of astronomy. Gravitational wave detectors, both ground-based and spaceborne, aim to capture ripples from potential black hole mergers involving Sagittarius A. Such events would dramatically reshape the Milky Way's core, offering a once-in-a-cosmic-lifetime spectacle. Sagittarius A is not just a distant, enigmatic object, it is a fundamental component of our cosmic story. Its study bridges astronomy, physics, cosmology, and even philosophy. As we gaze into the night sky, we look not just at stars but into a profound mystery that challenges and inspires, revealing the deepest workings of the universe. Sagittarius A continues to intrigue scientists because of its role as a cosmic laboratory where the laws of physics are pushed to their limits. The extreme environment around it provides an unparalleled opportunity to test Einstein's theory of general relativity. Near this supermassive black hole, gravity is so intense that space and time are warped in extreme ways, creating phenomena such as gravitational redshift and time dilation, where time itself passes differently compared to regions farther away. One of the most remarkable confirmations of general relativity near Sagittarius A came from observations of a star named S2. This star orbits the black hole in a highly elliptical orbit, coming within just 17 light-hours of Sagittarius A at its closest approach. By tracking its motion with exquisite precision over decades, astronomers witnessed the gravitational redshift predicted by Einstein. The star's light stretched to longer wavelengths as it moved through the intense gravitational field. This was direct evidence that spacetime behaves exactly as predicted by relativity, even in one of the universe's most extreme gravitational environments. The very discovery of Sagittarius A is a testament to humanity's growing ability to peer into the cosmic darkness. In the 1970s, radio astronomers using early interferometry techniques detected a bright, compact radio source at the center of the Milky Way. This source was designated Sagittarius A, named after the constellation Sagittarius, where the galactic center lies. Later, the more compact and intense core of this radio source was called Sagittarius A, revealing a far more exotic object at the galaxy's heart. Despite its importance, Sagittarius A remains remarkably faint compared to active galactic nuclei in other galaxies. This is largely because the Milky Way is a relatively quiet galaxy, with a low accretion rate, meaning the black hole is not actively devouring large amounts of matter. The faint emissions are still significant because they allow astronomers to study the physics of low luminosity accretion, offering insights into how black holes behave across different environments. Advancements in technology have revolutionized our understanding of Sagittarius A. Instruments like the Chandra X-ray Observatory and the Atacama Large Millimeter/Submillimeter Array, ALMA, have allowed us to observe high-energy flares from the black hole, sudden bursts of X-rays and radio waves that hint at turbulent processes in the accretion disk or magnetic reconnection events. These flares reveal a chaotic and dynamic environment where magnetic fields, hot plasma, and gravity interplay in complex ways. One of the most groundbreaking recent developments was the work of the Event Horizon Telescope collaboration, which achieved the first-ever image of a black hole's event horizon, in the galaxy M87. While Sagittarius A's image is more challenging due to its smaller size and more variable emission, efforts continue with even greater sensitivity and resolution. Imaging Sagittarius A directly would provide a powerful test of black hole models and could illuminate the precise geometry and structure of spacetime near the event horizon. The structure around Sagittarius A is not static. Gas clouds orbiting the black hole interact with the intense gravitational forces, sometimes stretching and compressing into intricate filaments and arcs. These clouds can collide, triggering shocks and heating gas to millions of degrees. The interaction between infalling matter and the black hole's magnetic fields may also launch relativistic jets, narrow beams of particles moving near the speed of light. Although Sagittarius A's jets are relatively weak compared to those of more active black holes. One of the biggest mysteries surrounding Sagittarius A is its formation. How did a black hole of several million solar masses come to reside at the center of our galaxy? Theories suggest it began as a smaller seed black hole formed from the collapse of a massive star or a cluster of stars. Over billions of years, it grew by accreting matter and merging with other black holes during galactic collisions. Understanding this growth helps illuminate the broader history of galaxy evolution. Sagittarius A is also closely linked to the dynamics of dark matter in the galactic center. While dark matter does not interact electromagnetically, its gravitational effects shape the orbits of stars and gas around the black hole. Some theories propose that dark matter may even accumulate near supermassive black holes, affecting accretion processes and possibly emitting exotic signals through particle annihilation. Looking ahead, future observatories and missions aim to unravel even more secrets. Projects like the James Webb Space Telescope will peer into the dusty heart of the Milky Way with unprecedented clarity in infrared wavelengths. Meanwhile, gravitational wave observatories such as LISA, Laser Interferometer Space Antenna, will open a new window onto the universe by detecting ripples in spacetime from events involving supermassive black holes, including Sagittarius A. Sagittarius A is more than a cosmic curiosity. It represents the nexus of physics, astronomy, and the story of our galaxy. As we continue to study it, we not only learn about black holes but also about the formation of galaxies, the life cycle of stars, and the fundamental laws that govern the universe. Each discovery about Sagittarius A brings us closer to understanding the nature of spacetime, matter, and the profound mysteries that lie at the very core of existence. Sagittarius A remains one of the most captivating objects in the cosmos because it challenges our perceptions about the nature of space, time, and matter. As a supermassive black hole, it sits at the intersection of multiple astrophysical disciplines, blending gravity, quantum mechanics, plasma physics, and high-energy phenomena into one enigmatic package. The layers of complexity that surround it reflect not only the intricacies of the universe but also the sophistication of human curiosity and technology designed to unveil these cosmic secrets. The environment immediately around Sagittarius A is dominated by extreme physics. The gravitational field is so strong that it bends light paths, an effect called gravitational lensing. Photons emitted by hot gas near the event horizon can be deflected and twisted, creating a ring-like structure known as the photon ring. This ring is crucial for direct imaging attempts because it marks the edge of the black hole's shadow, a boundary beyond which no information can escape. The accretion flow, the hot plasma spiraling into the black hole, is turbulent and magnetized. The interplay of magnetic fields and charged particles leads to complex behaviors including the generation of synchrotron radiation, a form of light emitted when electrons spiral at near-light speeds around magnetic field lines. These emissions dominate much of the radio and submillimeter signals detected from Sagittarius A, providing clues about the structure of the accretion disk and the magnetic environment near the event horizon. One of the most fascinating theoretical questions concerns the fate of information that falls into Sagittarius A. Classical physics suggested that information swallowed by black holes is lost forever, leading to what's known as the black hole information paradox. However, quantum theories propose that information must be conserved, sparking intense debates about how this could happen. Concepts like the holographic principle suggest that all the information absorbed by the black hole is somehow encoded on its two-dimensional event horizon, offering a revolutionary way to think about reality itself. Sagittarius A is also a key player in understanding galaxy formation and evolution on a cosmic scale. Observations across the electromagnetic spectrum show that many galaxies harbor supermassive black holes at their centers, and the masses of these black holes correlate with the properties of their host galaxies. This relationship, known as the M-sigma relation, implies a deep and fundamental connection between black hole growth and galaxy dynamics. Sagittarius A provides a local laboratory to study these processes in detail, linking small-scale physics to grand cosmic patterns. Moreover, the Milky Way's central black hole influences star formation rates in the nuclear region. By heating surrounding gas and injecting energy via winds or outflows, Sagittarius A can regulate the conditions for new stars to form. This feedback mechanism ensures a dynamic balance between the black hole's growth and the galactic environment, shaping the life cycle of the galaxy itself. Recent research has uncovered the presence of stellar remnants, neutron stars and stellar black holes, clustered around Sagittarius A. These dense objects are relics of massive stars that have ended their lives in supernova explosions. Their interactions with Sagittarius A's gravitational field and with each other create a gravitationally complex environment, possibly leading to mergers that produce gravitational waves. Detecting these waves would offer direct evidence of compact object collisions in the galactic center, adding a new dimension to our understanding. At a fundamental level, Sagittarius A also represents a testing ground for alternative theories of gravity. While Einstein's general relativity has withstood extensive scrutiny, certain observations, such as galaxy rotation curves, have motivated modified gravity theories and dark matter hypotheses. Precise measurements of stellar orbits and gravitational effects near Sagittarius A help constrain these theories, either reinforcing Einstein's framework or pointing to new physics. Astrophysical jets, a hallmark of many supermassive black holes, are less prominent at Sagittarius A. However, there is evidence of weak outflows and past episodes of jet activity, possibly linked to fluctuations in accretion rates. Studying these phenomena reveals how black holes transfer energy back into their environment, influencing galactic evolution and interstellar medium conditions. Looking further into the future, developments in multi-messenger astronomy promise to revolutionize the study of Sagittarius A. By combining electromagnetic observations with gravitational waves and neutrino detections, scientists aim to capture a more comprehensive picture of the black hole's behavior. Such approaches could unveil new aspects of matter under extreme conditions, particle acceleration mechanisms, and the dynamics of space-time itself. On a human scale, Sagittarius A embodies the spirit of exploration and the quest for knowledge. Its mysteries inspire technological innovation, from cutting-edge telescopes to advanced computational models simulating relativistic physics. It also evokes profound philosophical reflections on existence, the limits of observation, and the nature of reality beyond the visible universe. As our tools improve and our observations deepen, Sagittarius A will continue to be a beacon guiding us toward greater understanding. Each discovery peels back a layer of cosmic mystery, revealing a universe more interconnected and wondrous than previously imagined. In the heart of the Milky Way lies not only a supermassive black hole but a gateway to the fundamental truths of our cosmic origins and destiny. The center of the Milky Way, where Sagittarius A resides, is not merely a static location dominated by a single gravitational force. It is a realm of continuous activity, high-energy interactions, and dynamic transformations. Sagittarius A influences the structure, evolution, and energetic profile of the entire galaxy, not through visible light, but by its unseen power and subtle gravitational hand that orchestrates motion on the grandest of scales. This supermassive black hole, with a mass over 4 million times that of our Sun, exerts a powerful pull on everything in its vicinity. But unlike science fiction portrayals, it does not act as a cosmic vacuum indiscriminately sucking in all matter. In fact, its gravitational reach, while immense, is only dominant in the immediate galactic center. Farther out, the collective mass of stars, gas, and dark matter takes precedence. Nevertheless, the stability of the Milky Way's central region hinges upon Sagittarius A and its gravitational role. One of the ways we can observe Sagittarius A indirectly is through its influence on nearby stars, especially a specific group known as the S stars. These stars orbit extremely close to the black hole in highly elliptical paths, moving at speeds of thousands of kilometers per second. The most famous among them, S2, completes an orbit roughly every 16 years. The study of S2's orbit has confirmed predictions made by Einstein's general relativity to extraordinary precision. During its closest approach in 2018, scientists observed a redshift in its light due to the immense gravitational field, a direct demonstration of relativistic effects in real time. The existence of these fast-moving stars also provides insight into the density and compactness of Sagittarius A. No alternative theory, be it a cluster of dark stars, exotic particles, or a massive object composed of fermionic matter, can explain the gravitational influence on these stars as effectively as a black hole. Their movement serves as a dynamic tracer of the invisible behemoth lurking in the shadows. In addition to stars, Sagittarius A is surrounded by a swirling disk of gas and dust, though not as luminous or thick as those found in actively feeding quasars. This difference offers a unique window into low-luminosity accretion processes, a subject of great interest in astrophysics. The material in this disk gradually spirals inward due to angular momentum loss, emitting faint infrared and X-ray radiation as it heats up. However, much of the mass appears to be ejected before it can fall in, possibly due to winds or outflows driven by magnetic processes. What makes Sagittarius A truly fascinating is that it's not just a cosmic oddity. It may have once been much more active. Evidence in the form of giant bubbles extending above and below the galactic plane, called the Fermi bubbles, suggests that a powerful eruption occurred a few million years ago. These structures, glowing in gamma rays, span thousands of light years and are believed to have been powered by a past feeding frenzy of Sagittarius A. This event may have launched vast amounts of energy and plasma into space, creating shockwaves that continue to shape the galactic environment. In fact, X-ray observations of the central region reveal hot gas, ionized plasma, and echoes of past activity. Scientists have identified light echoes bouncing off surrounding gas clouds, relics of earlier flares that illuminate the galactic center's history like a cosmic time machine. These findings suggest that Sagittarius A has gone through active and dormant phases, alternating between quiet observation and violent outbursts. A remarkable aspect of studying Sagittarius A is how it bridges multiple disciplines. Its behavior cannot be fully understood through general relativity alone. Quantum mechanics must also be considered, especially when addressing the event horizon and what lies within. This fusion of the largest and smallest scales remains one of the biggest unresolved puzzles in modern physics. Theoretical physicists have proposed ideas like firewall hypotheses, fuzzballs, and Planck stars to reconcile black hole behavior with quantum theory. Each of these posits a different structure for the black hole interior or event horizon, potentially avoiding the information paradox and resolving contradictions in current models. Sagittarius A serves as a proving ground for such ideas, challenging us to build a theory of quantum gravity that seamlessly unites all forces of nature. Furthermore, Sagittarius A allows us to explore the concept of time dilation in extreme environments. Near its event horizon, time slows dramatically relative to observers farther away. If one could hypothetically hover just outside the event horizon, years could pass for them while millennia unfold in the outside universe. Though purely theoretical, this concept illustrates the mind-bending nature of space-time under intense gravity, making Sagittarius A living manifestation of Einstein's predictions. While direct observation of the event horizon is impossible due to its light-trapping nature, modern instruments have taken us closer than ever. The Event Horizon Telescope, EHT, an international collaboration connecting radio observatories across the globe, produced the first image of a black hole in 2019. That image, of the black hole in galaxy M87, paved the way for the imaging of Sagittarius A in 2022. Despite the difficulties, like interstellar scattering and rapid variability of its light, the EHT succeeded in capturing a blurry yet groundbreaking image of our galaxy's central monster. That image, a ring of glowing matter surrounding a dark shadow, confirmed decades of theory and placed our own Milky Way at the forefront of black hole research. The shape, size, and intensity of the image matched predictions from general relativity, reinforcing our confidence in the physics governing black holes. But it also raised new questions. Why does Sagittarius A behave differently from M87 despite similar structures? What causes its intermittent flares? How do changes in accretion rates influence observable properties? These questions drive the next generation of studies. Missions like the James Webb Space Telescope, the upcoming 30-meter telescope, and space-based X-ray observatories will enhance our ability to monitor Sagittarius A in real time, across wavelengths and scales. With each data point, we refine our models, adjust our equations, and broaden our understanding. Sagittarius A, though relatively quiet compared to distant quasars, is the best laboratory we have to study black holes up close. Its proximity allows for unparalleled detail. Its complex environment challenges our assumptions. Its mysteries stretch our theories to the breaking point. And its revelations promise to reshape how we understand the universe, from its earliest moments to its ultimate fate. To stand at the edge of such an object, mathematically, conceptually, or observationally, is to gaze into the unknown. A singularity lies hidden within, where our laws of physics collapse and certainty gives way to paradox. Yet even as we reach toward this darkness, we illuminate it with the light of human insight. Despite its terrifying nature and seemingly impenetrable veil of darkness, Sagittarius A is not a place of silence. In fact, its environment crackles with radio waves, X-rays, infrared signals, and sometimes sudden flares that surge through space like cosmic warning signs. These bursts of energy, often brief and fleeting, have puzzled astronomers for decades. What triggers them? Are they signs of matter falling into the black hole, or are they eruptions of magnetic energy akin to solar flares on our own sun, but on a far more massive scale? The answers lie in meticulous observation. Using instruments like NASA's Chandra X-ray Observatory, the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, scientists have tracked the variability of Sagittarius A's emissions. What they have found is a kind of pulse, a fluctuating heartbeat in X-rays and infrared light. Some days the black hole is quiet, on others, it flares up for hours, dramatically increasing in brightness before fading again into obscurity. These emissions are not consistent, nor are they entirely predictable, which makes them one of the most tantalizing aspects of the black hole's behavior. One prevailing theory suggests these flares may be caused by the accumulation of magnetic energy in the hot gas orbiting the black hole. As the gas moves, its charged particles twist magnetic fields into chaotic loops. When these magnetic field lines snap and reconnect, a process known as magnetic reconnection, they release tremendous amounts of energy, just as solar flares do on the Sun. This process could account for the sudden outbursts we observe from Sagittarius A, lighting up the galactic center in energetic wavelengths. Yet another potential source of flares is the tidal disruption of small celestial bodies, perhaps asteroids or comets, that wander too close. As these objects pass through the immense gravity field of the black hole, they are torn apart. Their debris is rapidly heated and compressed, releasing energy before vanishing from sight. Such events are rare and difficult to confirm but remain a viable explanation for some of the more intense flaring activity observed. The center of the Milky Way is not only home to Sagittarius A but also to an intricate and lively ecosystem of stars, clouds, magnetic fields, and high-energy particles. Surrounding the black hole is a region known as the Central Molecular Zone, a complex network of dense molecular clouds containing the raw material for star formation. Despite the hostile radiation and gravity, this region hosts a surprising number of young, massive stars, an astronomical oddity given the usual challenges to star birth in such extreme environments. These stars, some of which form what is called the clockwise disk, due to their coherent rotation pattern, offer additional evidence of Sagittarius A's influence. The gravitational forces needed to mold such organized motion around a central point strongly support the presence of a massive, compact object, our black hole. Some astronomers even suggest that the formation of these stars might have been triggered by interactions with material in the accretion disk of Sagittarius A, compressed and ignited by the gravitational influence. Meanwhile, at a more zoomed-out perspective, Sagittarius A plays a role in the dynamic behavior of the entire galaxy. Galactic bars, elongated features of stars and gas that funnel material inward, may serve to deliver matter to the central region, feeding the black hole sporadically over cosmic time. These inflows can spark episodes of activity, sometimes resulting in powerful outbursts that reshape the surrounding interstellar medium. Indeed, the impact of Sagittarius A may reach far beyond the galactic nucleus. When it was more active in the past, its emissions and outflows could have helped regulate star formation across large regions of the Milky Way. This process, known as AGN, active galactic nucleus feedback, is thought to be a crucial element in the evolution of galaxies. In large elliptical galaxies and quasars, such feedback can suppress the formation of stars by heating or expelling gas. Though Sagittarius A is currently in a low luminosity state, past evidence such as the Fermi bubbles indicates it once played a more dramatic role. The detection of these massive gamma-ray structures, towering tens of thousands of light-years above and below the galactic plane, offers a cosmic footprint of ancient violence. These bubbles may have formed from jets of energy launched by Sagittarius A millions of years ago, similar to those seen in active galaxies today. Alternatively, they could be the result of starburst activity, but their symmetric shape and alignment with the galactic center hints strongly at a connection with the black hole. Understanding these structures requires a combination of observational astronomy, computational modeling, and theoretical physics. Scientists simulate the complex physics of gas dynamics, magnetic fields, and relativistic particles to recreate how such bubbles might form. By comparing these models with actual observations from Fermi, Chandra, and other telescopes, researchers slowly piece together the black hole's ancient past, constructing a timeline of events that spans millions of years and stretches across the galaxy. Even more fascinating is the notion that we may be living in a calm period, a lull between cosmic tempests. Sagittarius A might awaken again in the distant future, perhaps triggered by an infalling cloud of gas or the passage of another massive star. If such an event were to occur, the central region of the Milky Way could once more blaze with X-rays and radio waves, the black hole entering an active phase that would transform the sky. One such event nearly occurred in 2014, when astronomers tracked a mysterious object dubbed G2, originally believed to be a gas cloud, on a collision course with Sagittarius A. Predictions ranged from total disruption to a minor feeding event. But as G2 made its closest approach, it surprisingly survived. Subsequent observations revealed that G2 may be a star shrouded in dust rather than a simple cloud. Its passage provided valuable data on the conditions near the event horizon, but the much-anticipated fireworks did not materialize. Nevertheless, the excitement surrounding G2 underscored our growing ability to monitor the galactic center in real time. Each close encounter, each flare, each anomalous behavior adds a piece to the puzzle. Sagittarius A may be difficult to observe directly, but its presence is never silent. It whispers through gravity, speaks through light, and occasionally roars with energies that traverse the galaxy. Moreover, Sagittarius A serves as a touchstone for cosmological principles. The very fact that it exists validates our understanding of gravitational collapse, stellar evolution, and the role of black holes in galactic architecture. And yet, it also beckons us toward deeper mysteries. What happens inside the event horizon? Is information truly lost, or is there a hidden mechanism by which it is preserved? Could there be wormholes or quantum bridges within? These are not merely science fiction speculations. They are questions that dominate theoretical physics today. The idea of black holes being gateways to other universes, or containing remnants of past cosmic epochs, captures the imagination not only of scientists but of anyone who has ever looked at the stars and wondered what lies beyond. Sagittarius A is more than just a region of space. It is the gravitational heart of the Milky Way, the anchor around which our galactic story unfolds. It has shaped the past, influences the present, and may determine the future. And as our tools become sharper and our minds more curious, the black hole at the center of everything may one day surrender its secrets. Its very existence challenges our understanding of space and time, not only in terms of observable astrophysics, but also in the realms of the abstract, where mathematics, philosophy, and theoretical physics converge. Sagittarius A is more than just a location, it's a cosmic boundary, where the known universe meets the unknowable. As we peer into this frontier, we are confronted with some of the most profound questions ever posed by humankind. What happens to time near a black hole? Can space itself be so drastically distorted that the laws we take for granted, those that govern energy, matter, and causality, begin to break down or transform into something entirely new? Sagittarius A is our closest laboratory to explore such frontiers. It is the one place where Einstein's theory of general relativity meets its greatest test, under the most extreme gravitational conditions nature can provide. Time dilation near the event horizon of Sagittarius A is not a hypothetical, it's a real, measurable effect. If one could hover near the edge of the event horizon, time would pass much slower relative to someone far away, say, on Earth. This is not just a theoretical curiosity. It has consequences for the flow of information and the very structure of reality. The closer you are to the black hole, the more you are stretched not only physically but temporally, suspended in a moment, while the universe continues without you. This leads us to perhaps the most poetic and mysterious feature of Sagittarius A, the event horizon. This is the surface beyond which nothing, not even light, can escape. Once an object crosses this threshold, it is effectively erased from the observable universe. And yet, its information, its history, its mass, its quantum properties, must somehow be accounted for. This is the infamous black hole information paradox, a dilemma that has baffled physicists for decades. Does the information get destroyed? Does it get encoded in some way on the surface of the black hole? Or does it get released via Hawking radiation in a scrambled but recoverable form? Hawking radiation itself, predicted by the legendary physicist Stephen Hawking, offers a glimpse into how quantum mechanics might reconcile with general relativity. According to this theory, black holes aren't truly eternal. They slowly evaporate over time, losing mass via quantum processes at the event horizon. For a supermassive black hole like Sagittarius A, this evaporation would take longer than the current age of the universe by many orders of magnitude. But the very idea that such a massive and seemingly permanent object could one day vanish introduces deep philosophical and scientific implications. Could Sagittarius A eventually die? If so, what happens to the Milky Way when the gravitational anchor at its center disappears? Would it alter the galaxy's structure or dynamics? These are long-term questions, ones measured in billions of years, but they illustrate the influence and importance of Sagittarius A not just as an astronomical object, but as a temporal cornerstone of our galaxy's lifespan. The black hole's surroundings also serve as a testing ground for exotic phenomena. Researchers have proposed that near the event horizon of Sagittarius A, quantum gravity effects could manifest. Some theoretical frameworks suggest the presence of a firewall, a searing wall of energy that incinerates anything crossing the event horizon. Others argue for a fuzzball model, wherein the black hole is a tangled mass of strings as described by string theory, without a traditional event horizon at all. Each model represents an attempt to unify the physics of the very large, relativity, with the physics of the very small, quantum mechanics, something science has yet to fully achieve. Sagittarius A is a cosmic Rosetta Stone, offering clues to such unification. But interpreting those clues requires not only observational advances but also revolutionary thinking. It demands interdisciplinary collaboration, bringing together astronomers, quantum theorists, computational scientists, and mathematicians. And even then, the answers may remain elusive, hidden behind the curtain of the event horizon, teasing us with glimpses and shadows. Yet, our progress is undeniable. From the early 20th century notions of compact dark masses, to the first compelling radio signals in the 1970s, to the breathtaking image captured by the Event Horizon Telescope in 2022, the path to understanding Sagittarius A has been one of relentless curiosity and ingenuity. The EHT image itself was a feat of global coordination, combining data from observatories on multiple continents, synchronizing atomic clocks, and reconstructing an image from terabytes of radio wave information. That blurry but iconic orange ring, shaped like a glowing donut, was more than just a scientific triumph. It was a symbol of humanity's ability to reach across space, time, and technological limits to confront the unknown. That image did not just prove that Sagittarius A was a black hole, it proved that we can witness the edges of spacetime itself. We saw, not the black hole directly, but the radiation from its surroundings bent and magnified by the immense curvature of space. It was a moment of both arrival and anticipation. What else might we be able to see if our instruments improve? What new secrets will emerge as we refine our vision? The next generation of observatories promises even greater clarity. Projects like the Next Generation Very Large Array, (NGVLA), and upgrades to the EHT aim to increase resolution, sensitivity, and the ability to capture dynamics in real time. Soon, we might be able to observe the motion of plasma in near orbit, see flares in unprecedented detail, and even track the rotation of the black hole's spin axis. Spin, in fact, is a topic of great interest. A black hole can spin, just as stars and planets do, but when it spins, it drags spacetime along with it. This phenomenon, known as frame dragging, means that space itself is twisted around the black hole. Determining the spin rate of Sagittarius A would yield critical information about its history, such as whether it formed from a single collapse or through successive mergers with other black holes. Some data suggests that Sagittarius A is spinning relatively slowly compared to its mass, which may support the idea that it has been relatively undisturbed for billions of years. Other models suggest periodic feeding events, when clouds or stars add mass and angular momentum. Pinning down this value remains one of the key goals in black hole astrophysics. Another mystery concerns the possibility of intermediate mass black holes in the galactic center. These would be smaller than Sagittarius A but still massive, perhaps thousands of solar masses. Finding them could help explain how supermassive black holes form, whether they grow gradually from smaller black holes or emerge quickly from the collapse of massive primordial structures in the early universe. There is even the tantalizing idea that Sagittarius A may not be alone. Some models propose the presence of a binary black hole system at the center of the galaxy, perhaps remnants of a past galactic merger. If true, this would revolutionize our understanding of the dynamics at play. Detecting such a system would likely require measurements of gravitational waves or minute shifts in stellar orbits. And speaking of gravitational waves, Sagittarius A may be a source of them, albeit subtle and rare. When black holes merge, they ripple spacetime itself. If Sagittarius A were to absorb a sizable black hole, the resulting waves could potentially be detected by future space-based observatories like LISA, Laser Interferometer Space Antenna. Such an event would offer a real-time glimpse into the birth of a more massive singularity, and the violent ballet of extreme gravity. Yet for all its drama, Sagittarius A also serves as a quiet reminder of cosmic patience. It evolves on scales far beyond human lifetimes. Its flares may occur over hours or days, but its major transformations take millions, if not billions, of years. Studying it is both a challenge and a privilege. It forces us to think beyond the now, to embrace the vastness of time and space, and to accept that some answers may lie just beyond our reach, waiting for future generations to uncover them. Sagittarius A anchors not just our galaxy, but our imagination. It is a cosmic oracle, both silent and eloquent, whose every photon tells a story and whose darkness challenges our light. As we continue to explore it, we are also exploring ourselves, our limits, our hopes, and our unyielding desire to understand the universe we inhabit. Even as we uncover more about Sagittarius A, the questions seem to multiply rather than diminish. This is the nature of deep cosmic inquiry. Each answer opens a dozen new doors. What lies beyond those doors is unknown, but Sagittarius A is at the heart of that exploration, an anchor not just in space but in our journey through scientific discovery. As observational tools sharpen and computational models grow more sophisticated, our understanding of black hole accretion processes is undergoing a renaissance. The environment around Sagittarius A is particularly turbulent, featuring shock waves, magnetic reconnections, and chaotic interactions among particles heated to billions of degrees. This seething cauldron of energy is not only a challenge to simulate accurately but also a treasure trove of information for understanding plasma physics under extreme gravitational conditions. What happens to magnetic fields in this kind of environment? How do they influence the inflow of matter, or the ejection of high-speed jets? Sagittarius A lacks the large, prominent jets seen in more active galaxies, but the mechanisms may still be present in miniature, providing insight into dormant or low-luminosity black holes. High-resolution simulations have revealed that accretion disks, flattened, rotating structures of infalling matter, do not simply swirl neatly into the black hole. Instead, they are warped, fragmented, and often governed by magnetic turbulence. These disks give rise to variability in brightness and emissions, observable as flares and pulses across the electromagnetic spectrum. Instruments like the Chandra X-ray Observatory and the Very Large Telescope have tracked these flares, each one offering clues to the invisible hand of gravity sculpting the behavior of matter and light. Even more puzzling are the so-called hot spots, observed near the event horizon. These are regions of intense brightness thought to be the result of clumps of matter orbiting at relativistic speeds. These hot spots offer a unique opportunity. By tracking their motion, astronomers can map the space-time geometry around Sagittarius A with remarkable precision. It's akin to watching glowing sparks dance around a drain, revealing the contours of a whirlpool invisible to the eye. In this case, the whirlpool is gravity itself, bending and shaping the path of everything nearby. Another source of fascination is the possibility of Sagittarius A housing exotic structures like boson stars or gravastars. While current data supports the standard black hole model, alternative theories have proposed objects that mimic black holes but lack singularities. Boson stars, composed of hypothetical particles known as bosons, would possess mass and gravitational pull but may not collapse into a singularity. Gravastars are theorized as having a shell of energy surrounding a void of dark energy, providing an alternative endpoint to gravitational collapse. Though these ideas remain speculative, Sagittarius A is an ideal testing ground, pushing the boundaries of both observation and theory. On a grander scale, Sagittarius A serves as a reference point for galactic dynamics. The Milky Way is not static, it's a rotating, spiraling structure influenced by dark matter halos, galactic arms, and interactions with satellite galaxies like the Magellanic Clouds. At the heart of it all, Sagittarius A provides gravitational coherence. Without such a central anchor, the stars in the bulge and the inner disk might drift or disperse. Its immense gravity tethers the inner galaxy, maintaining order in a chaotic cosmic ballet. Intriguingly, this central influence may extend into regulating star formation rates. Some researchers suggest that the activity or inactivity of supermassive black holes could influence the cooling of gas in galaxies, thereby promoting or suppressing the birth of new stars. While Sagittarius A is currently quiescent compared to the monstrous quasars found in distant galaxies, it may have had periods of increased activity in the past. Evidence of past outbursts, such as massive bubbles of high-energy particles extending above and below the galactic plane, suggest that Sagittarius A once had a more voracious appetite. These so-called Fermi bubbles, discovered via gamma-ray observations, extend tens of thousands of light-years and bear the signature of an energetic explosion millions of years ago. What caused this outburst? Was it a sudden feeding event, where Sagittarius A consumed a large amount of matter? Was it an ejection from magnetic processes in the accretion disk? Or could it have been the merging of black holes? Whatever the cause, these bubbles serve as a fossilized record of Sagittarius A's energetic history. There's also growing interest in how Sagittarius A affects the dark matter halo surrounding the Milky Way. While dark matter remains invisible and elusive, its gravitational influence is undeniable. Some theories propose that dark matter might interact differently near a black hole, perhaps concentrating or being disrupted in measurable ways. These interactions could leave signatures in the orbits of stars, in gravitational lensing, or even in the timing of pulsars. Speaking of pulsars, these rapidly rotating neutron stars with precise beams of radiation are valuable tools for testing gravity. If a pulsar were found in a tight orbit around Sagittarius A, it would allow unprecedented tests of general relativity. Pulsar timing is so accurate that any deviation caused by gravitational time dilation or space-time curvature could be detected. While we haven't yet found such a pulsar, astronomers remain hopeful. New radio surveys and instruments may reveal one in the coming decades, offering a new lens through which to observe the unseen. As we look further into the future, the study of Sagittarius A is poised to benefit from not only better instruments, but also new strategies and data analysis. Machine learning and artificial intelligence are being deployed to sift through mountains of observational data, finding patterns that may elude the human eye. These tools can optimize the alignment of telescopes, predict observational windows, and even simulate black hole environments with increasing realism. The future of astrophysics will be shaped not just by telescopes and satellites, but by algorithms and computational models that can interpret the cosmos in more nuanced ways. And what of the philosophical implications? Sagittarius A confronts us with a cosmic mirror. It is a place where light ends, where time twists, and where causality itself may unravel. For millennia, humanity has gazed at the stars seeking meaning. Now we gaze at a black hole, a region of space where nothing escapes, and find meaning not in what is emitted, but in what is absorbed. In its silence, Sagittarius A speaks volumes. It reminds us that the universe is not only more complex than we imagine, it is more complex than we can imagine. Every scientific paper, every radio signal, every simulated flare, and every blurry image of Sagittarius A is a note in an ongoing symphony of discovery. We are still composing that music, still deciphering the harmony of gravity, matter, and time that plays out at the heart of our galaxy. The study of Sagittarius A is more than a scientific endeavor. It is a human story, one of wonder, curiosity, and relentless pursuit of the truth. And so we continue to observe, to hypothesize, to test, and to dream. The black hole at the center of our galaxy is not a void, it is a beacon. It draws us in, not to destroy, but to reveal. It tells us that even in the darkest places, there is knowledge. Even at the edge of space-time, there is discovery. And even in the heart of nothingness, there is everything. We return now to that dense and enigmatic region of space-time where all known physical laws are pushed to their extremes. Sagittarius A, while invisible to our naked eyes, is anything but absent. It is active in silence, it moves without motion, and it dominates its environment through the curvature of space-time itself. Every new discovery we make about it does not just unravel a mystery, it presents a paradox. And with each paradox, we gain a clearer sense that our current understanding of physics is both powerful and incomplete. One of the most mind-bending aspects of Sagittarius A is its singularity, the point at which all its mass is thought to be compressed into an infinitely small space. According to general relativity, the singularity is a region of infinite density and zero volume, where the gravitational field becomes infinitely strong and time ceases to have meaning. Yet such infinities are signs not of ultimate understanding, but of the limits of our current theories. Physicists widely suspect that a theory of quantum gravity, one that unites general relativity with quantum mechanics, is needed to truly understand what lies at the center of a black hole. But as of now, that theory remains elusive. Many of the brightest minds have proposed frameworks to bridge this divide. String theory suggests that the fundamental constituents of matter are not particles, but tiny vibrating strings, and these could offer a way to smooth out the singularity. Loop quantum gravity, another contender, proposes that space itself is made of discrete loops, eliminating the idea of a singular point and replacing it with a granular structure of space-time. Could Sagittarius A contain the first natural laboratory for testing these ideas? Perhaps, but we must first find a way to observe what currently cannot be seen. One indirect approach is to study the quantum properties of Hawking radiation, a theoretical prediction made by Stephen Hawking in the 1970s. According to this theory, black holes can emit radiation due to quantum effects near the event horizon, eventually evaporating over vast periods of time. For a black hole like Sagittarius A, which is several million times the mass of the Sun, this evaporation process would take longer than the current age of the universe by many orders of magnitude. So while we can't observe Hawking radiation from it directly, the theoretical implications of such processes remain foundational to our understanding of black hole thermodynamics. Hawking's work also opened the door to the black hole information paradox. The question of whether information that falls into a black hole is lost forever or somehow preserved. Quantum mechanics insists that information cannot be destroyed, while classical interpretations of black holes suggest that it is. This paradox has spawned decades of debate, giving rise to exotic theories such as the holographic principle, which proposes that all the information contained within a three-dimensional region of space can be represented on its two-dimensional boundary. In other words, the universe, including Sagittarius A, might function like a vast cosmic hologram. What does this mean for the information consumed by Sagittarius A over billions of years? Is it encoded somehow on the event horizon? Is it transformed or stored in ways we don't yet understand? Or does our entire framework for what information means need to evolve? These are not questions with easy answers, but they are essential if we wish to reconcile the fundamental tenets of physics. Sagittarius A has also brought into sharp focus the limits of our observational capacities. While instruments like the Event Horizon Telescope and gravity have pushed the frontier, they still grapple with the immense challenge of distance, resolution, and noise. The Milky Way's core is obscured by thick clouds of gas and dust, making optical observation nearly impossible. That's why radio, infrared, and X-ray telescopes are so critical. They pierce through the shrouds that would otherwise block our view. And yet, even with all this technological progress, what we see is still more like a silhouette than a portrait. But this silhouette is rich with clues. By studying how light bends around Sagittarius A, how it flares and dims, how stars wobble and spiral in response to its gravitational pull, we are slowly mapping the unseen. It is like piecing together a puzzle using only the shadows it casts. Every star in its orbit, every photon bent, every ripple of gravitational waves tells a story about the invisible colossus at our galactic heart. In the coming decades, next-generation observatories like the 30-meter telescope, the square-kilometer array, and space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, will vastly increase our ability to study Sagittarius A. These tools will allow us to measure gravitational effects with unprecedented precision, perhaps even capturing real-time images of matter falling into the black hole. We may also detect the subtle effects of frame dragging, a phenomenon where space-time itself is twisted by the rotation of a massive object, predicted by general relativity, but only observed in limited contexts so far. Such observations will also help us understand how Sagittarius A interacts with dark energy and dark matter. While we know these components dominate the universe's mass-energy content, we have virtually no understanding of how they behave near extreme gravitational environments. Could Sagittarius A be influencing the local distribution of dark matter? Could it be warping the fabric of space in ways that affect our broader models of cosmic expansion? As with so many questions in astrophysics, the key may lie in the detailed study of the extreme. Furthermore, Sagittarius A stands as a cosmic time capsule. Every star that orbits it, every flare that bursts from its vicinity, carries the history of billions of years. The stars closest to it are among the oldest in the galaxy, remnants from a time when the Milky Way was young. Their composition, motion, and interaction with the black hole offer a glimpse into the galactic past. Studying them is not just an exercise in stellar dynamics, it's a form of galactic archaeology. And as we ponder these immense scales of time and space, it's easy to forget that Sagittarius A also helps answer deeply human questions. Where do we come from? What is our place in the cosmos? Are we alone? While Sagittarius A cannot speak to our emotional experience, it anchors the structure that makes life in the Milky Way possible. Its presence stabilizes the inner galactic disk. It influences the flow of interstellar gas. It may even play a role in the conditions necessary for planetary systems like ours to form. In this sense, Sagittarius A is not just a black hole, it is a cosmic foundation. And as we continue to learn more, it becomes clear that this single point of immense gravity, this mysterious void of unyielding pull, may hold the key to understanding everything from the birth of galaxies to the nature of reality itself. It is almost paradoxical that the most powerful object in our galaxy, Sagittarius A, is also one of the most hidden. This paradox is what fuels scientific curiosity and drives astronomers to push technological and theoretical boundaries. If we could somehow journey closer to it, not just through telescopic eyes or simulations but with a spacecraft equipped with instruments hardened for extremes, we might finally witness what lies just outside the veil of the event horizon. However, this is no ordinary voyage. This is a dive into an abyss where time dilates, space contracts, and the normal rules of the universe begin to fall apart. Imagine a probe approaching Sagittarius A. As it nears the event horizon, strange phenomena would occur. The immense gravitational pull would stretch light into longer wavelengths, a process called gravitational redshift, making the surroundings appear darker and darker. Time on board the spacecraft would slow down relative to an outside observer. A minute for the probe could be years or even centuries outside. This concept, predicted by Einstein's relativity, is not just theory, it has been measured in less extreme environments, like the GPS systems that need to account for time differences caused by Earth's gravity. But near a supermassive black hole, these differences become extreme. Near Sagittarius A, time itself warps to a crawl. Now picture that same probe's instruments capturing flares of X-rays and radio waves emitted from the accretion disk, the swirling, superheated matter that orbits just outside the event horizon. These flares are not random. They pulse and change, sometimes growing brighter and then fading. They might be the last breath of a star torn apart by tidal forces or magnetic interactions in the plasma. Each flare contains valuable data. By decoding these signals, scientists can infer the black hole's spin, its magnetic field strength, and even the distribution of mass around it. One particularly fascinating observation is the way matter behaves when it crosses the innermost stable circular orbit, the point of no return before plunging into the black hole. This orbit isn't a hard boundary, but a precarious edge. Beyond it, any object or light cannot remain in a stable orbit and will inevitably fall inward. Detecting this boundary indirectly helps researchers estimate the spin of Sagittarius A. If the black hole is spinning rapidly, the innermost stable orbit is closer to the event horizon. If it is spinning slowly, the orbit lies farther out. The evidence so far suggests that Sagittarius A may indeed be spinning, although not at the maximum rate allowed by relativity. Understanding the spin of a black hole is crucial because it influences everything around it: the accretion disk's shape, the way jets are launched, and the amount of energy that can be extracted from its rotation. This leads us to another captivating concept, the Penrose process. Proposed by physicist Roger Penrose, this theoretical mechanism allows energy to be extracted from a rotating black hole. In this scenario, a particle enters the ergosphere, the region just outside the event horizon where spacetime itself is dragged by the black hole's spin. Within this region, particles can split, with one falling into the black hole and the other escaping with more energy than it started with. Though never observed directly, such a process might power some of the jets we see blasting out of other black holes at nearly the speed of light. Sagittarius A, however, doesn't currently produce large jets. It's relatively quiescent compared to some of its active galactic nucleus, AGN, cousins in other galaxies. Yet, that may not have always been the case. There is compelling evidence that Sagittarius A was far more active in the past. Fermi bubbles, gigantic structures of high-energy gas extending tens of thousands of light-years above and below the galactic plane, may be remnants of a time when our black hole devoured a vast amount of matter, emitting powerful radiation in the process. This ancient activity, though long past, still influences the structure of the Milky Way. It may have helped shape galactic evolution and redistributed star-forming materials. How could Sagittarius A go from dormant to active again? All it would take is the right meal, a gas cloud or star that ventures too close. In 2013, astronomers tracked a gas cloud called G2 as it approached the black hole. Predictions were dramatic. G2 might be torn apart, feeding Sagittarius A and lighting up the center of the galaxy. But surprisingly, the event was anticlimactic. G2 passed by relatively unscathed, and the black hole barely reacted. This puzzled scientists. Some now believe G2 may have been a dense star cloaked in gas, rather than just a cloud. Others suggest the black hole is more selective, reacting only when truly massive meals are available. Events like these show just how dynamic and unpredictable Sagittarius A can be. We often think of black holes as static objects, sitting in the dark, consuming anything in their path. But in truth, they are responsive to their environment. They interact with stars, magnetic fields, and interstellar gas. They flare, sleep, awaken, and perhaps even merge with other black holes. In fact, one of the most exhilarating prospects in black hole astrophysics is detecting a future merger involving Sagittarius A. Such an event would unleash an enormous burst of gravitational waves, ripples in spacetime first predicted by Einstein and finally detected in 2015 by LIGO. A merger involving Sagittarius A would be on an entirely different scale. It would release more energy in a few seconds than all the stars in the galaxy combined over millions of years. Detecting such a wave would not only confirm theories of general relativity in extreme conditions, but it could help refine our models of galactic formation and growth. This leads us to the larger context. Every galaxy we observe seems to have a supermassive black hole at its center. And many of these are proportional in mass to the size of their host galaxy. This mysterious relationship, known as the M-sigma relation, suggests a deep connection between galaxies and their central black holes. But which came first? Did black holes form as a result of galaxy formation, or did they help spark it? It's a cosmic chicken and egg problem. Some theories propose that supermassive black holes formed very early in the universe, serving as seeds around which matter accumulated to form galaxies. Others suggest they grew slowly over time, fed by galactic material and mergers. The search for answers has led scientists to probe ancient galaxies, looking back billions of years with powerful telescopes like the James Webb Space Telescope. And what they've found is astonishing. Massive black holes already existed less than 1 billion years after the Big Bang. These primordial giants may be the ancestors of today's supermassive black holes, including Sagittarius A. Studying them not only tells us about the early universe but also how the black holes we observe today came to be. Back at the center of our own galaxy, Sagittarius A remains a sentinel. Not only does it anchor the Milky Way gravitationally, but it also acts as a guardian of cosmic secrets. Its extreme conditions provide a testbed for physics under circumstances that can't be replicated in any lab on Earth. Each flare, orbit, and burst offers a chance to probe the laws of nature, to challenge our understanding of space, time, energy, and matter. It also forces us to confront existential questions. If black holes can warp time and store information in ways we don't yet comprehend, what does that say about our universe? Are we living in a holographic projection? Is the fabric of space truly smooth, or is it made of discrete units we have yet to detect? Could black holes, like Sagittarius A, be windows into other dimensions, or gateways to realms beyond our current grasp? These are not merely speculative questions. They are the very edges of human understanding. And standing on that edge, looking into the gravitational abyss, is Sagittarius A, immovable, unfathomable, yet somehow familiar. It is the mystery at the heart of our home, the quiet titan that binds our galaxy together, the puzzle that may one day reveal the most profound truths about reality itself. And so, the journey continues deeper, beyond the observable, beyond the predictable, into the boundless realms of theory, imagination, and perhaps even revelation. For Sagittarius A, this supermassive black hole sitting silently at the heart of the Milky Way is not simply a cosmic object. It is a symbol, a representation of the unknown, of everything we do not yet understand, and everything we hope to uncover. When scientists point their telescopes at the galactic center, they are not just observing a region in space, they are peering into the crucible of cosmic truth. Sagittarius A challenges the limits of our physics. General relativity describes gravity on large scales, and quantum mechanics governs the tiny world of particles. Yet black holes represent the place where these two theories collide. Here, our equations falter. Our certainty dissolves. This is where humanity meets the edge of its knowledge. Take, for example, the concept of Hawking radiation. Proposed by Stephen Hawking in 1974, this theory suggests that black holes are not completely black. Quantum fluctuations near the event horizon could cause particle-antiparticle pairs to appear, with one falling into the black hole and the other escaping. To an external observer, this looks like radiation being emitted by the black hole. If true, this process could cause the black hole to slowly lose mass over time and eventually evaporate. But for Sagittarius A, with its enormous mass, over 4 million times that of the Sun, this process would take far longer than the current age of the universe to significantly affect it. Nevertheless, the idea itself is revolutionary. It connects black holes with thermodynamics, entropy, and the fundamental nature of information. And that brings us to the black hole information paradox. According to quantum mechanics, information about physical systems cannot be destroyed. Yet, if matter carrying information falls into a black hole, and the black hole eventually evaporates into featureless Hawking radiation, then that information seems to be lost. This leads to a contradiction between two core principles of physics. It's a paradox that has baffled scientists for decades. Some theorists argue that information is somehow encoded in the Hawking radiation. Others suggest that information is preserved on the event horizon itself, giving rise to the holographic principle, the idea that the three-dimensional information inside a black hole is encoded on its two-dimensional surface. Sagittarius A is at the heart of this debate, metaphorically and physically. It's the closest laboratory we have for testing these bold ideas. Although we can't currently detect Hawking radiation from it, its temperature is far colder than the cosmic microwave background. We can refine our theories by watching how matter behaves in its extreme environment. The behavior of plasma, the flickering of light, the motion of orbiting stars, all of these are breadcrumbs left for us to follow. But even more intriguing is the possibility that Sagittarius A might one day become the site of a gravitational experiment so extreme, so profound, that it redefines our understanding of time and space. Imagine if two black holes merge near the center of the Milky Way. The collision would produce gravitational waves of unprecedented strength. Detectors like LIGO and Virgo might feel the echoes, but future missions like the Laser Interferometer Space Antenna, LISA, a space-based observatory, could record the event in exquisite detail. These gravitational waves could act like a fingerprint, revealing not only the masses and spins of the merging black holes but also whether general relativity holds up under the most extreme conditions. Such a future merger is not pure fantasy. Our galaxy has absorbed many smaller galaxies in its history. Some of those galaxies may have carried their own central black holes. As these remnants spiral inward, drawn by gravity, they may one day collide with Sagittarius A. The process would take millions of years, but in the long arc of cosmic time, such events are inevitable. Each merger would feed and grow the central black hole, adding to its mass and perhaps changing its spin, transforming it slowly over eons. And yet, for all the drama and gravity and chaos that Sagittarius A represents, it is also a stabilizing force. It holds the galaxy together, anchoring the orbits of stars, clusters, and gas clouds. Without its immense gravitational pull, the structure of the Milky Way would be very different. Spiral arms might not hold their shape. Stars could drift away. Planetary systems, including our own, might not remain stable. Even our Sun, distant as it is from the galactic center, is part of the vast orbital ballet choreographed by Sagittarius A. Our solar system orbits the center of the galaxy roughly once every 230 million years, in a vast, elliptical path that takes it through regions of varying density and stellar activity. And each time we complete this galactic orbit, Sagittarius A is there, unseen, unfelt, but ever present, a cosmic metronome keeping time. Beyond astronomy, Sagittarius A holds philosophical weight. It is a reminder of our place in the universe. It evokes awe, humility, and wonder. How can something so immense exist in silence, hidden behind a curtain of stars and dust, visible only through its influence on the objects around it? How can a region smaller than the orbit of Mercury wield such power? And if a black hole can exist at the heart of our galaxy, what might exist beyond? Are there even stranger objects, naked singularities, boson stars, gravastars, yet to be discovered? Are the laws of physics, as we know them, incomplete? Might black holes be gateways to parallel universes, as some string theorists suggest? Could Sagittarius A be connected to other black holes through Einstein-Rosen bridges, wormholes, waiting to be unlocked? Such questions push the boundaries of imagination. And while they remain speculative for now, they fuel a deeper curiosity, one that drives scientists to build better telescopes, more sensitive detectors, more powerful simulations. Missions like the Event Horizon Telescope are already producing groundbreaking results. The 2019 image of the black hole in M87 was only the beginning. In 2022, the same global collaboration released the first image of Sagittarius A's shadow, a blurry but historic glimpse of the monster in our midst. That image was the result of years of work, combining data from radio telescopes around the globe to form a planet-sized observatory. The challenges were immense. Sagittarius A is smaller and more dynamic than M87's black hole, meaning that the light around it changes more quickly. Capturing a stable image required not just cutting-edge technology, but also sophisticated algorithms to reconstruct the data. It was a triumph of science, engineering, and collaboration. And it's just the beginning. Future upgrades to the Event Horizon Telescope could sharpen our view, revealing more structure, more detail. We may be able to see the rotation of matter, the shape of magnetic fields, the warping of space itself. Other observatories, both ground-based and spaceborne, will complement this data, providing a multi-wavelength view of Sagittarius A. The European Southern Observatory's extremely large telescope, ELT, scheduled to come online soon, will deliver unprecedented optical resolution. Space missions like Athena and Lynx will probe high-energy X-rays. Together, these instruments will weave a rich tapestry of observation, each thread bringing us closer to understanding. And in this ever-evolving mosaic, Sagittarius A remains our greatest teacher. Silent, ancient, unknowable, and yet central to everything we are. In the heart of the galaxy it waits, a cosmic oracle carved from gravity and mystery, pulling not just stars and gas into its orbit, but our dreams, our questions, our future. Let us continue our deep descent into the cosmic abyss that is Sagittarius A, the shadowy, mysterious core of the Milky Way, where our best science meets its greatest challenges. To understand Sagittarius A is to confront the very fabric of reality itself. For it is not simply a black hole, but a nexus point, where time, space, matter, energy, and even meaning are twisted together in an intricate dance governed by laws we have only begun to decipher. One of the most stunning aspects of Sagittarius A is its profound influence on the structure and behavior of the galaxy on a grand scale. Despite being so distant from us, about 26,000 light-years away, its presence determines the layout of the Milky Way's spiral arms. As a supermassive black hole, its mass anchors the orbits of billions of stars, including our Sun. But its role isn't passive. Sagittarius A may have played a key part in shaping the galaxy's past, its formation, its periods of growth, its bursts of star formation, and even its moments of dormancy. But black holes are not just gravitational wells. They are also extreme engines of feedback. Sagittarius A, while relatively quiet now, may have been much more active in the past. Evidence suggests that a few million years ago, Sagittarius A went through a period of high-energy outbursts. These ancient flares likely sent powerful winds of radiation and charged particles shooting out into the galaxy, altering the conditions for star formation across vast distances. One of the most striking clues comes in the form of the Fermi bubbles, two massive, balloon-like lobes of gamma radiation stretching about 25,000 light-years above and below the galactic plane. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these structures suggest that Sagittarius A erupted in a colossal outburst sometime in the past, releasing energy on a scale that dwarfs anything humanity could produce. What triggered this outburst? It might have been a sudden infall of gas, perhaps from a passing cloud or a disrupted star, funneled into the black hole's accretion disk. As matter spirals inward, it becomes superheated, emitting intense radiation before disappearing past the event horizon. During this chaotic process, magnetic fields are twisted and charged particles are flung outward at nearly the speed of light. The result is a temporary but titanic brightening, turning Sagittarius A into an active galactic nucleus, a quasar-like beacon that briefly dominated the galactic core. Today, Sagittarius A is relatively dormant. But dormant does not mean dead. It still feeds, albeit sporadically. Occasionally, a clump of gas or dust strays too close, igniting a burst of X-rays or infrared radiation detectable by space telescopes like Chandra and Spitzer. These flares, while far less energetic than the ancient outbursts that formed the Fermi bubbles, offer a window into the accretion physics of black holes and the dynamics of material in extreme environments. Every flicker, every pulse of radiation tells a story of magnetic fields, turbulent plasmas, relativistic speeds, and gravity so strong that even light bends in submission. The environment around Sagittarius A is rich with clues. The galactic center is a crowded and chaotic region. It teems with stars, gas clouds, and dense star clusters. There are exotic objects there that don't behave like anything else in the galaxy. Some stars orbit Sagittarius A at incredible speeds, tracing out tight ellipses over just a few years. These so-called S-stars are among the best evidence we have for the presence of a compact, massive object at the center. One star in particular, S2, orbits every 16 years and approaches within just 17 light hours of the black hole, about 3 times the distance from the Sun to Pluto. By tracking S2 and similar stars, astronomers can map the gravitational potential in exquisite detail. These observations have confirmed the predictions of general relativity, showing that the paths of these stars precess, or shift slightly, just as Einstein's theory predicts in the warped spacetime around a massive object. But these stars do more than confirm relativity, they offer a testing ground for new physics. Some researchers are watching for deviations that could hint at dark matter, extra dimensions, or modifications to gravity. Others are probing the potential of exotic objects near the black hole, things like magnetars, superdense neutron stars with magnetic fields trillions of times stronger than Earth's, or the mysterious G objects that seem to blur the line between star and gas cloud. These strange entities are on eccentric orbits that bring them dangerously close to Sagittarius A, yet somehow they survive, defying expectations. And speaking of strange, we must also consider the question of what lies beyond the event horizon. Classical general relativity says it's a singularity, a point of infinite density where the curvature of spacetime becomes infinite, and the known laws of physics cease to apply. But many physicists believe that this singularity is only an artifact of our incomplete understanding. Quantum gravity, a theory that would unify general relativity with quantum mechanics, might smooth out this singularity, replacing it with something else, a core of finite size, a quantum remnant, or even a gateway to another universe. This is where black holes touch the edge of the metaphysical. If Sagittarius A does not merely end in a singularity, but instead conceals deeper structure, it could serve as a laboratory for understanding the very nature of space and time. It could help resolve the black hole information paradox by showing how information is stored and retrieved. It could provide insights into the early universe, where similar conditions might have existed. Some even speculate that black holes could be the seeds of new universes, cosmic eggs whose interiors birth new realms of space-time. Such ideas remain speculative, but they are not without merit. Theoretical work in loop quantum gravity and string theory continues to explore these possibilities. Meanwhile, efforts to detect subtle quantum effects, such as the aforementioned Hawking radiation or gravitational wave echoes, could offer the first empirical evidence for new physics. Of course, much remains unknown. Sagittarius A is a riddle with layers upon layers of complexity. Every discovery seems to open new questions. What causes the erratic flares of light we observe? Why do some stars cluster tightly around the black hole while others avoid it entirely? How did such a massive object form so early in the galaxy's history? Was it seeded by the collapse of a giant primordial star? Did it grow through the merger of smaller black holes? Or was it born in some more exotic way, perhaps from a dense cloud of dark matter? These questions drive observational campaigns across the electromagnetic spectrum. Infrared telescopes peer through the dust to track stellar motions. Radio observatories capture the jet-like outflows and synchrotron radiation. X-ray and gamma-ray satellites scan for high-energy flares. And gravitational wave detectors await the tremors of cosmic collisions. Each wavelength reveals a different facet of the same reality. Together, they create a multidimensional portrait of the most mysterious object in our galactic neighborhood. And even here, near the end of what we know, we return again to the beginning. To that first moment when a photon, bent by gravity, reached our instruments and whispered of something unseen. To the first flicker of infrared light from a speeding star. To the realization that deep in the darkness at the heart of the Milky Way lies not emptiness, but a presence, a vast, silent engine that shapes the very structure of our world. Sagittarius A is a gravitational anchor, a cosmic mystery, a source of energy, a relic of ancient activity, a test of fundamental physics, and possibly, a gateway to truths beyond our current grasp. It is the embodiment of both what we know and what we yearn to discover. Its study demands the full range of human ingenuity, physics, astronomy, mathematics, philosophy, and imagination. As we continue our exploration of Sagittarius A, we find ourselves stepping not just into the domain of black hole physics, but into the very heart of what it means to investigate the unknown. The fascination with this supermassive entity at the core of our galaxy is not solely a scientific endeavor, it is a profound human quest. We are driven by curiosity to understand something we can never touch, never visit, and never escape from once crossed. Yet, from a distance of 26,000 light-years, we have unraveled truths that stretch the limits of perception. Let us return to the environment immediately surrounding Sagittarius A, which is perhaps one of the most exotic neighborhoods in the entire cosmos. Here, physics takes on an otherworldly flavor. The region is populated by a mix of phenomena: high-velocity stars, compact remnants, dense molecular clouds, streams of plasma, and radiation fields that vary in frequency and intensity. This is the inner parsec, the last light year before the gravitational abyss. It's a place where time slows, space curves sharply, and energy erupts with little warning. It is, for lack of a better word, wild. And yet, within this chaos, there is structure. There is an accretion disk, an extended, flattened ring of matter that spirals toward the event horizon. This disk is composed of gas and dust that have been shredded from other objects, perhaps pulled off of passing stars or from nearby molecular clouds. As this material accelerates inward, it heats up to millions of degrees, emitting X-rays and gamma rays before vanishing forever. The disk is turbulent, governed by magneto-hydrodynamic processes, where magnetic fields tangle, reconnect, and release massive amounts of energy. Understanding this environment requires not only Einstein's equations, but also advanced plasma physics and fluid dynamics. Just outside this disk lie stars with some of the most extreme orbits in the known universe. The aforementioned S stars are not alone. Researchers have now catalogued dozens of such stars, each moving in response to the invisible pull of Sagittarius A. The trajectories of these stars are not static. They evolve, shift, and precess over time, influenced by relativistic effects that subtly warp their paths. These shifts offer a laboratory for testing general relativity under conditions that are otherwise impossible to replicate. For instance, one of the key predictions of Einstein's theory is the gravitational redshift, an effect in which light emitted from a strong gravitational field is stretched, shifting toward the red end of the spectrum. In 2018, astronomers observed this effect directly in the light coming from star S2 during its closest approach to Sagittarius A. The star's spectral lines were visibly redshifted beyond what would be expected from simple motion alone, confirming once again that Einstein's insights hold up even in the presence of a supermassive black hole. But general relativity is not the only theory being put to the test. Sagittarius A serves as a proving ground for new models of quantum gravity. One idea being explored is that the event horizon might not be a true horizon at all. Instead, it could be a fuzzy or firewall-like boundary created by quantum effects. In such scenarios, matter falling into a black hole wouldn't simply vanish, it might encounter violent quantum turbulence, or even bounce back into the universe in some altered form. Though no such effects have yet been observed, the region around Sagittarius A offers the best chance we have of someday detecting them. And then there is the question of spin. All black holes are expected to rotate, and Sagittarius A is no exception. Measuring this spin is notoriously difficult, but it is crucial to understanding the black hole's history and future behavior. A rotating black hole drags spacetime around with it, a phenomenon known as frame dragging. This effect can alter the orbits of nearby objects and the behavior of accretion disks and jets. While estimates of Sagittarius A's spin vary, it is believed to be moderate, fast enough to affect its surroundings, but not so fast as to produce an extremely narrow ergosphere or jet. Speaking of jets, their absence is another point of interest. Many active galactic nuclei exhibit spectacular jets, columns of particles and energy that shoot out along the black hole's axis of rotation, stretching for thousands of light years. Sagittarius A, however, lacks a prominent jet. Some weak radio outflows have been detected, but nothing on the scale seen in quasars or radio galaxies. This suggests that either the black hole's spin is insufficient to produce such structures, or that the accretion disk is misaligned, disrupting jet formation. Alternatively, it may simply be a matter of timing, that we are observing the black hole during a dormant phase in its cycle of activity. Another fascinating feature of the galactic center is its population of compact objects. Black holes, neutron stars, and white dwarfs are expected to be concentrated near Sagittarius A, drawn in by its immense gravity over billions of years. However, directly detecting these objects is challenging, especially given the dense gas and dust that obscures visible light. Radio observations and X-ray surveys are beginning to uncover a population of these remnants, which could number in the tens of thousands. These objects not only provide insights into the end states of stellar evolution, but they may also interact with each other in exotic ways, potentially forming binaries that merge and emit gravitational waves. Indeed, the potential for gravitational wave detections from this region is immense. As detectors like LIGO, Virgo, and the future LISA mission improve, we may soon be able to pick up the ripples of space-time caused by compact object mergers near Sagittarius A. These signals would carry encoded information about the masses, spins, and trajectories of the merging objects, as well as about the surrounding gravitational environment. Gravitational wave astronomy offers a new sense, a way to hear the universe, complementing our ability to see it through electromagnetic radiation. But even with all of this, we are only scratching the surface. The galactic center is full of mysteries waiting to be unraveled. There are the G objects, peculiar bodies that exhibit both the characteristics of stars and gas clouds. They appear to stretch and deform near Sagittarius A, as if they are being torn apart, yet they somehow remain intact over time. Their true nature remains debated. Are they the bloated envelopes of merging stars? Are they newborn protostars wrapped in dense cocoons? Or are they something entirely new? And what about the strange periodic radio signals that have occasionally emanated from the galactic center? These mysterious pulses have puzzled astronomers for years. While some of them have been attributed to known sources like magnetars, others remain unexplained. Could they be the signatures of new types of neutron stars, or even something more exotic like boson stars, hypothetical objects made of dark matter particles? Or could they hint at new physics? Even more speculative are theories that propose the existence of a dark matter spike near Sagittarius A. According to some models, the intense gravity of the black hole should have drawn in and concentrated surrounding dark matter over billions of years, forming a steep density gradient around the core. If such a spike exists, it could enhance the signals of dark matter annihilation or decay, potentially making the galactic center a prime target for indirect dark matter detection. But as always, we must temper our speculation with data. That is why missions like the Event Horizon Telescope, EHT, are so critical. In 2022, the EHT collaboration released the first image of Sagittarius A's event horizon, the shadow cast by the black hole against the glowing background of infalling material. This image, while blurry by everyday standards, is a triumph of modern science. It confirms that Sagittarius A has the structure we expect from a Kerr black hole, a rotating, relativistic object with a well-defined shadow. And yet, even this image leaves much room for interpretation. Variability in the light curve, asymmetries in brightness, and shifts in polarization all offer new windows into the dynamics of space-time. The EHT team continues to refine its data, improving resolution and coverage by adding more telescopes and using more sophisticated algorithms. Future observations will provide time-lapse movies of the black hole's behavior, allowing us to watch matter move and spiral in real time. These observations will deepen our understanding of accretion physics, magnetic fields, and general relativity under extreme conditions. At the same time, the James Webb Space Telescope is poised to revolutionize our understanding of the galactic center in the infrared. With its unparalleled sensitivity and resolution, JWST can peer through the dust and reveal the population of stars and protostars forming near Sagittarius A. It can detect the chemical signatures of molecules in the accretion disk, shedding light on the conditions near the event horizon. It may even discover entirely new classes of objects, things we never imagined because we had no way to see them. In every direction we look, radio, infrared, X-ray, gravitational waves, we find more reasons to be captivated by Sagittarius A. It is not just a black hole. It is a crucible of cosmic evolution, a testbed for our theories, a window into the early universe, and perhaps even a door to deeper truths. To study Sagittarius A is to engage in one of the most profound scientific adventures of our time. And we are far from done. As our journey deeper into the heart of Sagittarius A continues, the complexity of this enigmatic region only grows more profound. It's easy to imagine a black hole as a simple concept, a point in space where gravity is so strong that nothing can escape. But in truth, Sagittarius A is anything but simple. It is a cosmic symphony of matter, energy, magnetism, and space-time, interacting in ways we are only beginning to comprehend. Let's now shift our attention to the strange effects of time and space near the event horizon. According to general relativity, time near a massive object passes more slowly relative to observers farther away, a phenomenon known as gravitational time dilation. Near Sagittarius A, this effect becomes extreme. An object orbiting close to the event horizon would experience seconds while years pass in the wider universe. If you were to watch this object from a safe distance, it would appear to slow down, freeze, and fade as it approached the edge of the black hole. This is not an illusion, it's a real warping of time itself, a direct consequence of curved space-time. This distortion has real implications. It means that processes near the event horizon are essentially recorded in slow motion to distant observers. It also suggests that if any information or light is emitted during a plunge into the black hole, that information is stretched out over enormous periods, making the event horizon appear like a one-way membrane to the outside universe. This leads us to one of the most profound puzzles in modern physics, the black hole information paradox. The information paradox challenges the very foundations of physics. Quantum mechanics insists that information is never lost. It can be transformed, scrambled, hidden, but not destroyed. Yet black holes seem to defy this. Once matter crosses the event horizon, it disappears forever. If the black hole evaporates through Hawking radiation, as theory predicts, then all the information it contains seems to vanish. This violation of unitarity, a key principle of quantum theory, is unacceptable to physicists, and so the race to resolve the paradox is one of the most intense in theoretical physics today. Sagittarius A, being the closest supermassive black hole, may offer the key to unraveling this paradox. While we cannot observe information falling into the black hole directly, we may be able to study the properties of Hawking radiation, subtle echoes in spacetime, or correlations in the surrounding magnetic field that hint at how information is encoded or released. Some theories suggest that the event horizon isn't a sharp boundary but a chaotic, quantum, fuzzball, where information is preserved in an exotic state. Others propose that spacetime itself breaks down near the horizon, allowing for some form of information escape. Meanwhile, the energetic environment around Sagittarius A provides another route to understanding high-energy astrophysics. The shock waves, particle acceleration, and turbulence near the accretion disk resemble conditions thought to exist in the early universe. By studying the emissions from this region, particularly in the gamma-ray and X-ray bands, we can learn about the most energetic processes known to science. These include synchrotron radiation, where electrons spiral around magnetic fields at near-light speeds, and inverse Compton scattering, where photons are boosted to higher energies by colliding with fast-moving particles. In this environment, magnetic fields play a dominant role. They twist, reconnect, and erupt in flares, brief bursts of high-energy radiation that have been observed repeatedly coming from Sagittarius A. These flares are among the most powerful emissions in the galaxy, and their unpredictable nature adds another layer of intrigue. Some flares may be triggered by sudden drops of matter into the accretion disk, while others could be magnetic explosions, not unlike solar flares but on a much larger scale. The polarization of this radiation provides another window into the workings of Sagittarius A. Polarization describes the orientation of light waves, and it is influenced by the magnetic fields and plasma conditions through which the light travels. By mapping this polarization, astronomers can reconstruct the structure of the magnetic field lines around the black hole. This was one of the triumphs of the Event Horizon Telescope, which produced the first polarized image of Sagittarius A, showing a swirling pattern that reveals the complex interplay of forces near the event horizon. Yet even as we unlock these secrets, we are haunted by deeper questions. What lies beyond the event horizon? Is it a singularity, a point of infinite density and zero volume where known physics collapses? Or is it something stranger still, perhaps a gateway to another region of spacetime, a wormhole, or even a passage to another universe? While these ideas remain speculative, they are grounded in mathematical possibilities offered by general relativity and quantum field theory. Some physicists have proposed that black holes could be holograms, with the information of everything they consume encoded on the event horizon like pixels on a screen. This idea is part of the broader holographic principle, which suggests that all the information contained within a volume of space can be represented on its boundary. If true, Sagittarius A would not be a void, but a storage device of staggering capacity, archiving the history of everything that has ever fallen into it. Others believe that quantum entanglement plays a key role. Perhaps the interior of the black hole is connected to the exterior by quantum links, Einstein's so-called spooky action at a distance. These connections might allow information to escape subtly, encoded in correlations between Hawking radiation particles or in disturbances to the surrounding vacuum. Then there's the idea of Planck stars, a hypothesis in loop quantum gravity suggesting that the singularity is replaced by a dense core of Planck-scale matter. In this view, black holes might eventually rebound, releasing their contents in a new burst of creation. Could Sagittarius A be a ticking clock, destined to one day explode in a reverse Big Bang? Unlikely on human timescales, but theoretically possible. As incredible as these ideas sound, they are not science fiction. They are attempts to reconcile two of the greatest theories in physics, general relativity and quantum mechanics, within the crucible of the cosmos. And Sagittarius A is their testing ground. We are living in a golden age of black hole science. With new telescopes, better algorithms, and deeper theories, the mysteries of Sagittarius A are beginning to yield. But we are also reminded, with every discovery, of how much we still do not understand. The heart of our galaxy is a place where matter becomes energy, where time slows to a crawl, and where the fundamental nature of reality is rewritten. Sagittarius A is not just a gravitational monster lurking at the center of the Milky Way. It is a teacher, a paradox, a question mark written in the language of space and time. And as long as we seek to understand it, we will continue to learn not only about the universe, but about ourselves. The presence of Sagittarius A at the center of our galaxy forces us to grapple with the most profound elements of our existence. It is not merely a destination for infalling matter or a source of dramatic astrophysical activity. It is a monument to the very fabric of the universe, molded by forces so extreme that they defy common understanding. Every photon that escapes the gravitational grasp of this titanic object carries a story, a history of the swirling chaos around the event horizon, a tale of matter torn, stretched, and accelerated to near-light speed before vanishing forever into the cosmic abyss. As scientists refine their observational techniques, the behavior of matter near Sagittarius A becomes increasingly detailed. Consider the motion of gas clouds like G2, which passed remarkably close to the black hole in 2014. Observers expected G2 to be shredded and devoured, lighting up the galactic center in a brilliant flare. But instead, G2 survived the encounter, revealing an unexpected resilience. Some theorists now suspect that what appeared to be a simple gas cloud may in fact have concealed a star or compact object at its core, protected by its own gravity. These encounters are not just exciting, they are diagnostic. Each object that interacts with Sagittarius A provides more data points about the black hole's mass, spin, and the distribution of matter in the inner galaxy. And it is not only gas and stars that help illuminate the picture. High-energy particles, known as cosmic rays, also offer insights. Some of these particles may originate from near Sagittarius A, propelled outward by processes still not fully understood. By measuring their energies, compositions, and arrival directions, astrophysicists can trace them back to their potential sources, and Sagittarius A is a prime suspect. This leads us into the complex world of relativistic jets, high-speed outflows of plasma launched along the magnetic poles of some black holes. While Sagittarius A currently shows no large-scale jets, there is evidence it may have possessed them in the past. Observations of the surrounding galactic environment, including massive structures like the Fermi bubbles, vast lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane, suggest that Sagittarius A was far more active millions of years ago. These bubbles are likely the faded echoes of a quasar-like phase when Sagittarius A blazed with accreting material and launched powerful outflows into the galactic halo. Understanding whether Sagittarius A will flare to life again is one of the central goals of modern galactic astronomy. If the supply of matter into its accretion disk increases, say, due to a merger with another galaxy, or the infall of a large molecular cloud, the black hole could reignite, becoming a beacon visible across the cosmos. What would such an awakening look like? The sky would glow in X-rays and radio waves. The surrounding interstellar medium would heat and shift. And the Milky Way itself might evolve in ways we've never before witnessed. Of course, such changes take time, astronomical time. Even a rapid event in the vicinity of a black hole might unfold over thousands or millions of years. But this does not mean we are powerless to understand or predict. With each decade, our instruments grow more sensitive. Our computers grow more powerful. Our simulations grow more detailed. We can now model the behavior of spacetime near Sagittarius A with astounding precision, tracking the trajectories of virtual particles and predicting the gravitational lensing effects that distort light around the black hole. One of the most fascinating aspects of these simulations is their ability to visualize what cannot be seen. Using data from telescopes and theoretical inputs from general relativity, scientists can render images and animations of what Sagittarius A might look like from different angles and distances. These visualizations are not just pretty pictures, they are testable predictions. As observational capabilities improve, we can compare real data to simulations, refining our models and improving our understanding of black hole physics. In fact, one of the major breakthroughs of the Event Horizon Telescope was not just the imaging itself, but the comparison between theory and observation. The image of Sagittarius A's shadow, a dark region encircled by a glowing ring, matched closely with predictions from general relativity. This was a resounding confirmation that Einstein's theory remains valid even in the most extreme conditions imaginable. But it also raised new questions. Are there subtle deviations? Are there quantum effects we cannot yet detect? Could there be differences in spin, orientation, or magnetic field strength that escape our current instruments, but lie just beyond the horizon of technological progress? Even now, multiple teams around the world are refining their measurements of the black hole's spin. This is no easy task. Unlike mass, which can be measured by observing orbital dynamics, spin requires a detailed understanding of how spacetime is being dragged around the black hole, a phenomenon called frame dragging. In essence, a rotating black hole twists spacetime around it, like a spoon swirling molasses. This effect changes the shape of the accretion disk, alters the paths of photons, and influences the polarization of emitted light. By measuring these subtle clues, scientists hope to pin down just how fast Sagittarius A is spinning. Spin is not just an idle curiosity. It plays a critical role in black hole thermodynamics and jet formation. A highly spinning black hole can store more rotational energy, which can then be tapped by magnetic fields to power relativistic jets. It also influences the location of the innermost stable circular orbit, the closest distance that matter can orbit before plunging into the event horizon. For Sagittarius A, knowing the spin would help refine models of its past and future activity. It would also constrain theories of how the black hole formed and evolved. Did it grow slowly over billions of years? Or did it gain much of its mass early in galactic history through violent mergers? These questions extend to the broader context of galactic evolution. Sagittarius A is not an isolated monster, it is part of a dynamic, evolving galaxy. Its gravitational influence shapes the orbits of stars, the structure of the central bulge, and the flow of gas toward the center. In turn, the feedback from the black hole, whether in the form of jets, radiation, or winds, affects star formation, chemical enrichment, and the large-scale structure of the Milky Way. This feedback loop is now recognized as a fundamental driver of galaxy evolution throughout the universe. And it all centers around a point smaller than the orbit of Mercury, yet containing 4 million times the mass of the Sun. As we look to the future, new instruments promise to revolutionize our understanding of Sagittarius A. The upcoming James Webb Space Telescope, though focused on infrared observations, may be able to peer through the dust to study the central stars in unprecedented detail. Meanwhile, ground-based arrays like the 30-meter telescope and extremely large telescope will offer unparalleled resolution in the optical and near-infrared. Radio observatories like the next-generation Very Large Array will complement these efforts, providing exquisite detail of the radio environment. On the theoretical side, advancements in quantum gravity, string theory, and loop quantum cosmology may eventually yield a deeper understanding of what lies inside the event horizon, or even what came before. Could black holes be remnants of a prior universe? Could they spawn new universes through bound scenarios or quantum fluctuations? While such ideas remain speculative, they are increasingly explored with mathematical rigor, driven by the tantalizing mysteries of objects like Sagittarius A. At the same time, popular interest in black holes is at an all-time high. Films, documentaries, and books bring these cosmic behemoths into public imagination, and rightly so. There is something profoundly human about looking into the darkness at the center of our galaxy and asking, "What's there? What does it mean? Could we ever go there? And if we did, what would we find?" The answer is both awe-inspiring and humbling. For Sagittarius A is not just a physical object, it is a philosophical boundary, a challenge to our knowledge, a mirror to our own limitations. And yet, it also offers a frontier, a chance to expand our science, to question our assumptions, and to journey, through data, through theory, through imagination, to the edge of what is known. As we continue our journey into the depths of Sagittarius A, the importance of time becomes increasingly evident, not just in the practical sense of observing long-term cosmic changes, but in the profound relativity of time itself near a supermassive black hole. In Einstein's theory of general relativity, time is not absolute. It bends and stretches in the presence of mass and gravity. Near Sagittarius A, this distortion becomes extreme. Time itself slows down the closer one gets to the event horizon. For an outside observer, a spacecraft descending toward the black hole would appear to slow, its movements becoming increasingly lethargic, its light redshifted into longer and longer wavelengths. From the perspective of the traveler, however, everything would seem to proceed normally, until the moment they cross the event horizon, from which there is no return. This time dilation is not just a curiosity, it has real implications for astrophysics. The slowing of time affects how we perceive events around Sagittarius A. It changes how energy is emitted, how orbits are measured, and how data must be interpreted. Telescopes and models must account for these effects when constructing images or interpreting light curves. In a way, understanding Sagittarius A is as much about mastering the nature of time as it is about gravity and matter. This leads to another fascinating aspect of black hole physics, the event horizon itself. The event horizon is not a solid surface but a boundary in spacetime beyond which nothing, not even light, can escape. For Sagittarius A, this boundary lies at a radius of about 12 million kilometers from the center, according to the Schwarzschild solution for a non-rotating black hole of its mass. But if Sagittarius A is spinning, as many suspect, the true boundary is more complex. The shape becomes oblate, and the radius of the event horizon changes depending on the direction of approach. There is also an ergosphere, a region outside the event horizon where spacetime is dragged so strongly that no object can remain at rest. The ergosphere is one of the most exotic features of a spinning black hole, and it opens up theoretical possibilities such as the Penrose process, whereby energy could be extracted from the black hole's rotation. This process is highly speculative in a practical sense, but it serves as a tantalizing thought experiment for physicists exploring the boundaries of what energy means in a relativistic universe. Could advanced civilizations one day tap the rotational energy of black holes like Sagittarius A? Could black holes be used as power sources, as some have hypothesized in the framework of Kardashev Type 2 or 3 civilizations? Even more mind-bending is the possibility of black holes as portals. Some theories propose that the interiors of black holes might connect to other regions of spacetime, a concept known as a wormhole. While current evidence offers no support for this in Sagittarius A, the idea lingers in the speculative edge of physics. If such wormholes exist, they would require exotic matter with negative energy density to remain open. Such matter is not known to exist in stable quantities, but quantum field theory does permit fleeting regions of negative energy in phenomena like the Casimir effect. This raises the tantalizing but currently untestable question: could Sagittarius A hide something more than just a point of no return? Meanwhile, astronomers continue to map the orbits of stars near the galactic center to measure the influence of Sagittarius A with ever greater precision. The so-called S-stars, especially S2, have become vital tools in this effort. S2's 16-year orbit around the black hole has been tracked for decades, and in 2018, scientists observed the relativistic redshift in its light as it neared its closest approach. This was a milestone in observational astronomy, a direct confirmation of general relativity in the extreme gravity of a supermassive black hole. Future observations of other S-stars, including the discovery of potentially even closer ones, promise to deepen our understanding and test theories of gravity in ways previously impossible. Another frontier lies in gravitational wave astronomy. While the LIGO and Virgo detectors have primarily detected mergers of stellar mass black holes, the upcoming LISA, Laser Interferometer Space Antenna, mission, scheduled for launch in the 2030s, will open a new window on the universe. LISA is designed to detect lower-frequency gravitational waves from massive black hole mergers. If Sagittarius A ever merges with another supermassive black hole, perhaps during a future galactic collision, the resulting gravitational wave signal would be enormous, detectable from across the cosmos. Even before such an event, smaller compact objects spiraling into Sagittarius A, such as neutron stars or stellar mass black holes, could produce gravitational waves that LISA might detect. These events, called extreme mass ratio and spirals, EMRIs, are among the most promising targets for LISA and would offer a precise map of the black hole's space-time geometry. The notion that Sagittarius A could eventually merge with another supermassive black hole is not far-fetched. The Milky Way is on a collision course with the Andromeda Galaxy, scheduled to occur in roughly 4.5 billion years. When the two galaxies merge, their central black holes will likely form a binary system, orbit each other, and eventually coalesce. Such a merger would be one of the most violent events in cosmic history, releasing gravitational waves that ripple through the universe and possibly igniting a new phase of quasar-like activity. Studying Sagittarius A today is thus not just about the present, it is a preparation for the future, a way of setting benchmarks against which to measure the coming transformations of our galaxy. Another dimension to consider is the chemical and molecular environment near Sagittarius A. This region, known as the Central Molecular Zone, CMZ, is rich in complex molecules, turbulent clouds, and magnetic activity. Despite its proximity to the black hole, the CMZ is a site of ongoing star formation, albeit at a rate lower than expected. Understanding how this interplay works, how the black hole influences gas dynamics, star birth, and molecular chemistry, is one of the key goals of modern astrophysics. The strange balance between the gravitational pull of Sagittarius A and the turbulence of the CMZ may hold clues to how galaxies regulate their own growth. This regulation is a topic of great interest in the broader context of cosmic evolution. Observations of distant galaxies suggest that supermassive black holes and their host galaxies grow together, in a process called coevolution. The mass of the central black hole is strongly correlated with the mass of the galactic bulge, a relationship known as the M-sigma relation. This suggests a feedback mechanism in which the black hole influences star formation in the galaxy, and vice versa. For Sagittarius A, understanding this balance helps clarify the evolutionary path of the Milky Way itself. In terms of cosmic timescales, Sagittarius A is still young. While it has existed for billions of years, its current quiet phase may be temporary. Historical evidence, such as X-ray light echoes observed in molecular clouds near the center, suggests that Sagittarius A was more active just a few hundred years ago. These echoes are the lingering fingerprints of past flares, possibly caused by the infall of stars or gas clouds, and they provide a form of black hole archaeology that allows astronomers to reconstruct its recent history. This interplay between the past, present, and future of Sagittarius A is part of what makes it so compelling. It is a living laboratory, a place where time, space, matter, and energy collide in their most extreme forms. And yet, it is also a place of beauty, a cosmic dance of stars, a glow of radio light, a swirling maelstrom at the heart of the Milky Way. To study it is to touch the edge of the known and to gaze into the unknown. The study of Sagittarius A has also opened doors into one of the most elusive concepts in theoretical physics, the information paradox. At the heart of this paradox lies a simple but devastating question: what happens to information that falls into a black hole? According to quantum mechanics, information about the state of a system can never be truly destroyed. Yet classical interpretations of black holes, especially under general relativity, suggest that anything crossing the event horizon is lost forever, its physical properties crushed into an unknowable singularity. Stephen Hawking proposed that black holes could emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation, over vast time scales, would cause the black hole to evaporate and disappear. But if it disappears, where does the information go? If the radiation is purely thermal and carries no information, then information is truly lost, a violation of quantum mechanics. Sagittarius A, as a real-world example of a supermassive black hole, does not emit measurable Hawking radiation due to its enormous mass. Its temperature, based on Hawking's formulas, would be only fractions of a nanokelvin, colder than the cosmic microwave background. Nonetheless, it stands as the perfect natural laboratory to think through the implications of such paradoxes. Could information be encoded in the Hawking radiation somehow? Is it stored in some quantum form on the event horizon, as suggested by the holographic principle? The holographic principle posits that all the information contained in a volume of space can be represented as a theory on the boundary of that space, an idea that has transformed the way physicists think about gravity and quantum theory. In this view, the three-dimensional space inside the black hole might be a projection of information that lives on its two-dimensional surface. If this is true, then the secrets of everything that has fallen into Sagittarius A are not truly lost. They are just encrypted in a way we don't yet understand. This leads naturally into the concept of black hole entropy. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not the volume. This is shocking because it suggests that the information capacity of a black hole is limited not by how much it can contain inside, but by how much surface area its horizon has. For Sagittarius A, with its immense horizon, this means an astronomical entropy, a chaotic soup of all the physical states it has ever consumed. And yet, in its current quiet state, it sits in silence, revealing none of it. This contradiction between the silent appearance and the hidden complexity within Sagittarius A is what gives rise to one of the most controversial ideas in modern theoretical physics, the firewall paradox. Some physicists have proposed that instead of a smooth transition across the event horizon, as general relativity predicts, there could be a firewall of high-energy particles that burns up anything trying to cross. This idea violates the equivalence principle of general relativity but seeks to preserve the integrity of quantum mechanics. The existence of such a firewall would mean that black holes are not the serene gravitational vacuums we once thought, but that the boundary of Sagittarius A could be a violent, incinerating shell. As theoretical models multiply, so too do the instruments built to test them. The Event Horizon Telescope, which captured the first image of the black hole in M87, has since been turned towards Sagittarius A. Because Sagittarius A is smaller and closer, its event horizon appears roughly the same size in the sky as that of M87, but its variability presents unique challenges. The plasma and magnetic fields swirling around Sagittarius A change on the order of minutes, compared to the days-long variability in M87. This requires far more precise synchronization between the telescopes around the globe, each contributing to the interferometric array that creates the final image. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A's shadow, confirming the predictions of general relativity with stunning accuracy. The shadow, the dark region against the glowing plasma, revealed the shape of the photon ring, a circular boundary formed by light bending around the black hole. This ring is not a solid structure but a ghostly echo of light that has orbited the black hole multiple times before reaching our instruments. It's the signature of curved spacetime itself, and it is shaped by the mass and spin of the black hole. For Sagittarius A, the image confirmed its mass, its location, and its compactness. There is no doubt this is a black hole. But with this confirmation comes a new frontier. The EHT team is already planning upgrades. With new telescopes joining the array and improvements in bandwidth and sensitivity, future observations will offer sharper images, faster data collection, and possibly even dynamic videos of the changing accretion flow around Sagittarius A. Imagine seeing a time-lapse of gas swirling around the event horizon, perhaps capturing a flare in real time, or tracing the orbital motion of plasma clouds as they circle the abyss. Such visualizations are not only scientifically valuable, they are among the most profound human achievements, revealing to us a realm of reality that until recently was purely theoretical. Meanwhile, other telescopes like the Chandra X-ray Observatory and the Very Large Telescope continue to track emissions from Sagittarius A across the electromagnetic spectrum. X-ray flares, infrared flashes, and radio flickers all offer pieces of a larger puzzle. By correlating data from different wavelengths, astronomers can build a multidimensional picture of the environment near the black hole. They can track the energy release from magnetic reconnection events, map the inflow of matter, and perhaps even catch a star in its final moments, as it is spaghettified and consumed. One of the most intriguing events in recent years was the observation of a mysterious gas cloud, known as G2, which approached Sagittarius A in 2014. Many expected G2 to be shredded and consumed by the black hole, producing a dramatic increase in brightness. But the event turned out to be more subtle. G2 survived its encounter, suggesting that it may not have been a simple gas cloud, but rather a star shrouded in dust. This episode showed that our understanding of the region remains incomplete, and that even the most powerful gravitational force in the galaxy can still surprise us. And then there is the future. We are on the cusp of a new era in astrophysics, one in which Sagittarius A will no longer be an abstract concept or a blurred radio source. As observational techniques improve and theoretical models grow more sophisticated, the black hole at the heart of the Milky Way will become the centerpiece of some of the most advanced science ever conducted. Quantum gravity, dark matter, cosmic evolution, all of it flows through the singularity at the center of our galaxy. Yet for all our progress, Sagittarius A still guards its deepest secrets. We do not know what lies at its core. We do not know how to reconcile the infinite density predicted by general relativity with the quantum graininess of space-time suggested by loop quantum gravity or string theory. We do not know whether time ends at the singularity, or whether some bridge, some connection, stretches beyond it into another part of the cosmos. It remains an enigma, a question mark in the sky that beckons with both terror and beauty. And perhaps that is the most important truth of all. In Sagittarius A, we confront the limits of our understanding. We are forced to reckon with the boundaries of science, the places where equations fail and imagination begins. It is not just a black hole. It is a symbol of the unknown, of the frontier, of the endless pursuit of knowledge that defines us as a species. To study it is to confront the universe itself, and to admit that, for all we have learned, we have only just begun. Its gravitational pull is not only a localized phenomenon but a fundamental architect of the galaxy's structure. The Milky Way is a barred spiral galaxy, a majestic formation of stars, gas, dust, and dark matter organized into a central bar structure from which spiral arms extend. At the very center of this galactic dance is Sagittarius A, anchoring it all with its immense mass. The orbits of stars, clusters, and even the entire galactic disk are subtly shaped by this hidden monster. Over billions of years, its influence has helped determine which stars survive, which get consumed, and how matter flows within the galactic nucleus. Despite its terrifying nature, Sagittarius A is not a destroyer alone, it is also a regulator. Black holes are not merely gravitational sinks, they act as engines of feedback that can shape the evolution of entire galaxies. This feedback can come in many forms: radiation, jets, winds, and outflows that heat surrounding gas or prevent it from collapsing into new stars. While Sagittarius A is currently in a quiet phase, there is evidence that it wasn't always so passive. Studies of the Fermi bubbles, enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane, suggest a violent past. These structures, discovered by NASA's Fermi Gamma-Ray Space Telescope, are believed to have been created by a sudden, powerful outburst from the center of the galaxy, perhaps 1 million years ago. Such an event would have unleashed torrents of energy into the galactic halo, reshaping the environment and halting star formation across wide regions. This relic of ancient violence implies that Sagittarius A is capable of awakening, of shifting from a dormant guardian to an active disruptor. This dichotomy, between stillness and fury, is another core mystery of supermassive black holes. What causes them to flare up? Why do some, like quasars, blaze with unimaginable brilliance, while others, like Sagittarius A, slumber in near darkness? The difference may lie in the availability of fuel. A quasar is a galaxy whose central black hole is actively accreting matter, surrounded by a thick, hot accretion disk that radiates across the electromagnetic spectrum. If Sagittarius A were fed more material, by a wayward star, or a cloud of gas, it might ignite into such a beacon. But for now, it waits, occasionally flickering with small flares, reminders of the fire within. We also see echoes of this potential in the movements of stars around the black hole. Observations by the gravity instrument on the Very Large Telescope Interferometer have allowed scientists to measure the orbital motions of stars like S2 with unprecedented precision. These measurements have confirmed that the stars follow the paths predicted by general relativity, but they have also hinted at subtle deviations. These could be signs of perturbations by unseen objects, or even hypothetical forms of dark matter concentrated in the galactic core. One particularly tantalizing possibility is the presence of a dark matter cusp, a dense concentration of dark matter surrounding Sagittarius A. If dark matter particles are self-annihilating, their interactions near the event horizon could produce detectable gamma rays. While no such signal has yet been definitively observed, the region remains a prime target for future dark matter experiments. If Sagittarius A is indeed nestled in a halo of dark matter, it could serve as a cosmic laboratory for studying one of the most elusive substances in the universe. Moreover, there's growing interest in the idea that the supermassive black hole might host a population of intermediate mass black holes orbiting it, perhaps remnants of earlier galactic mergers. These black holes, with masses between stellar and supermassive, are the missing link in our understanding of black hole formation and growth. If they exist around Sagittarius A, they could gravitationally interact with nearby stars and gas, influencing the dynamics of the region. Detecting them would require precise astrometric and gravitational wave measurements, but the payoff could be monumental, revealing a whole new class of astrophysical object. And speaking of gravitational waves, Sagittarius A is a prime candidate for generating them. When massive objects spiral into it, such as stellar mass black holes or neutron stars, they emit gravitational waves that ripple through spacetime. These waves, too faint for current detectors, are the targets of future missions like the Laser Interferometer Space Antenna, LISA, a space-based observatory planned by ESA and NASA. With LISA, we may one day hear the death screams of stars falling into Sagittarius A, converting their mass into gravitational music as they vanish into darkness. Even further ahead, theorists dream of using quantum computers to simulate the environment near Sagittarius A, including the strange quantum effects that might dominate near the singularity. This would require a revolution in both hardware and algorithms, but the ambition reflects the stakes. The singularity represents a frontier where general relativity and quantum mechanics clash, where the known laws of nature cease to operate. Understanding it may lead to a grand unified theory of physics, one that describes the universe from the smallest particles to the largest structures. And then there is the philosophical dimension. What does it mean to have such an object at the heart of our galaxy? Not a star, not a cluster, but a void, a region where space itself collapses, and time has no meaning. It forces us to rethink our place in the cosmos. We orbit a star, which orbits the galactic center, which is anchored by a black hole. At every scale, we are governed by gravity, by invisible forces shaping our past and our future. In that sense, Sagittarius A is not just an astrophysical object, it is a cosmic mirror, reflecting the limits of our understanding and the limitless scope of our curiosity. And curiosity is what drives the next generation of astronomers, physicists, and engineers. Young scientists around the world are now being trained to work on Sagittarius A, not only to study it, but to use it as a gateway to deeper truths. Universities develop simulations, observatories refine their techniques, and theorists test bold new hypotheses, all centered on this invisible gravitational anchor. Children growing up today may live to see movies of Sagittarius A in motion, perhaps even 3D maps of its accretion disk, or real-time monitoring of flares and gas clouds. They may grow up in a world where black holes are no longer abstract, but mapped and monitored like weather systems. They may see artificial intelligence sift through petabytes of data, finding patterns in the noise, signatures of hidden phenomena, clues to new physics, perhaps even anomalies that rewrite our understanding of nature. As technology advances, so does imagination. Science fiction writers have long speculated about civilizations harnessing the energy of black holes, creating habitats around their accretion disks, or using them as gateways through space-time. While such visions remain speculative, the physics behind them is grounded in real theory. A spinning black hole can, in principle, be tapped for energy via the Penrose process, and the Einstein-Rosen bridge, a kind of theoretical wormhole, remains a tantalizing possibility, though likely unstable. Could Sagittarius A conceal such structures within its core? Could it be the key to faster-than-light travel, to time loops, to realms beyond the observable universe? These questions are not just the domain of dreamers. They motivate researchers in quantum gravity, loop theory, string theory, and other cutting-edge fields. They force us to ask what spacetime really is, whether it is smooth and continuous, or granular and emergent, like the pixels of a holographic screen. They drive us to build better instruments, to ask sharper questions, to dare to look deeper. And always, Sagittarius A waits. Silent. Dark. Unmoving. Yet at the same time, whirling with energy, flickering with quantum activity, wrapped in magnetic storms, its gravity guiding stars, its influence shaping the fate of everything around it. It is both emptiness and totality. It is the eye at the center of the storm. And in studying it, we study not just the universe, but ourselves. We study our own need to know, to push against the edges of the map, to ask what lies beyond the veil. Sagittarius A is not the end, it is a beginning. The beginning of a journey not into space, but into truth. The deeper we peer into the abyss that is Sagittarius A, the more we begin to realize that its existence is not merely a distant curiosity, but a living narrative, etched into the very fabric of the Milky Way and intimately entwined with our cosmic story. Each photon of light distorted by its gravity, each wisp of matter devoured by its maw, each star compelled to trace an elliptical path in its shadow, all paint a vivid picture of an object so utterly foreign to human intuition that it defies comprehension, yet invites obsession. The recent technological renaissance in astronomy has thrown open the door to unprecedented levels of observation. One of the most transformative breakthroughs came in 2022 when the Event Horizon Telescope collaboration released the first direct image of Sagittarius A's shadow, an iconic moment in science. This globe-spanning network of radio telescopes synchronized data with such precision that they achieved the resolution necessary to glimpse the event horizon of a black hole some 26,000 light-years away. What we saw was not the black hole itself. Its interior remains hidden forever, but the glowing, warped halo of gas and radiation tracing the boundary where light can no longer escape. That image was more than a scientific milestone. It was a symbol. It was humanity using a planet-sized eye to behold the heart of its own galaxy, capturing the place around which everything spins. It was a demonstration of cooperation across continents, cultures, and institutions, all in pursuit of a single goal: to look into the dark and understand. But that image, as remarkable as it was, opened as many questions as it answered. The shape and size of the shadow matched general relativity's predictions, yet subtle deviations may exist. Future observations, with improved sensitivity and resolution, aim to catch Sagittarius A in action, capturing the dance of hot plasma, the twisting of magnetic fields, and perhaps even transient flares as matter plunges toward the point of no return. Such flares have already been detected. Instruments like NASA's Chandra X-ray Observatory and the Very Large Telescope have recorded sudden bursts of X-ray and infrared light from Sagittarius A, each lasting a few hours. These are thought to arise from blobs of gas being accelerated to near light speeds before being devoured, heating to millions of degrees and radiating with lethal intensity. The flares give us fleeting glimpses of the feeding habits of this cosmic predator, snatches of behavior otherwise hidden behind layers of gas and dust. These sporadic outbursts might one day escalate. Astronomers closely monitored the passage of a gas cloud, G2, which in 2014 swung dangerously close to Sagittarius A. Initially, there were fears that G2 would be shredded and consumed, triggering a dramatic flare-up. Yet, surprisingly, the black hole remained mostly quiet. Some theorists now believe G2 may contain a hidden star or a cluster of planets, wrapped in a veil of gas. Others think it simply skirted too far from the danger zone. Regardless, its close call reminded the scientific community that Sagittarius A is not a static feature. It lives, breathes, and changes with time. And that time stretches across epochs. Sagittarius A has existed since the dawn of the galaxy, and perhaps even before. How it formed remains one of astrophysics' most tantalizing puzzles. Did it grow slowly, accumulating matter over billions of years? Or did it form from the collapse of a primordial gas cloud in the early universe? Some models suggest that the seeds of supermassive black holes were planted by the very first stars, giant, unstable behemoths that collapsed into massive black holes, which then merged and accreted material over cosmic timescales. Others propose more exotic origins, involving direct collapsed black holes or even relics of the Big Bang itself. Primordial black holes formed from density fluctuations in the infant universe. If any of these early black holes survived and grew, they might account for the presence of supermassive black holes like Sagittarius A in relatively young galaxies, even those seen just a few 100 million years after the Big Bang. Understanding this formation process is more than academic. It ties directly to the life cycles of galaxies, to the emergence of large-scale cosmic structures, and even to the behavior of dark matter. If supermassive black holes formed early, they could have served as scaffolds around which matter coalesced, accelerating the growth of galaxies. If they formed late, then they are consequences, not causes, of galactic formation. Either way, they are key actors in the great cosmic drama, silent titans shaping light and matter across the void. And as our understanding grows, so too does our ambition. The next generation of telescopes, the James Webb Space Telescope, the Extremely Large Telescope, the Square Kilometre Array, will probe deeper into the history of the universe and into the core of our own galaxy. They will study the interstellar medium near Sagittarius A, the distribution of stars in its immediate neighborhood, the strange orbits that defy simple gravitational models. Among the most promising frontiers is the study of general relativity in extreme conditions. Sagittarius A provides a near-perfect testing ground. It is massive enough to warp space-time dramatically, but close enough that we can track individual stars orbiting it over human timescales. Already, the motion of the star S2 has confirmed Einstein's predictions about gravitational redshift, the stretching of light by intense gravity. But future measurements may reveal subtler effects, frame dragging, precession, perhaps even signatures of alternative theories of gravity. Indeed, if general relativity breaks down anywhere, it will be near a black hole. Some physicists propose that inside the event horizon lies a fuzzball, a quantum tangle replacing the classical singularity. Others suggest that information falling into a black hole is encoded on its surface, the so-called holographic principle. These ideas seek to reconcile gravity with quantum mechanics, to unify the forces of nature into a single framework. And at the center of that endeavor stands Sagittarius A silent oracle whispering truths in equations we do not yet understand. But understanding is coming. Slowly, piece by piece, observation by observation, theory by theory. And as we pull back the curtain, we uncover not just the anatomy of a black hole, but the structure of reality itself. We discover how space can bend, how time can flow differently, how energy and mass can become indistinguishable. We learn that the universe is stranger and more beautiful than we ever imagined. And perhaps most humbling of all, we find our place in it. Not as masters of the cosmos, but as students. As creatures made of dust and curiosity, looking out from a fragile world toward the heart of the galaxy, and listening. Sagittarius A remains as it always has, a dark sentinel, a gravitational monarch, an enigma shrouded in math and mystery. But it is also a mirror. It reflects our hunger to know, to explore, to connect with the cosmos. It reminds us that even in the darkest places, there is light, scattered, warped, but never completely lost. And as long as we keep searching, keep building, keep questioning, we bring that light closer. We trace the curves of space-time, we decode the radiation, we refine the equations. And we step, one insight at a time, toward a universe in which black holes are not boundaries, but bridges. We return now to the region surrounding Sagittarius A, often referred to as the galactic center, a chaotic and breathtaking domain, saturated with complexity, both in terms of matter and motion. It is a stellar metropolis packed far denser than anywhere near Earth's location in the Milky Way. Here, stars orbit the black hole at speeds measured in thousands of kilometers per second. Clouds of ionized gas writhe and shimmer under the weight of tremendous gravitational forces, and massive magnetic fields swirl through the plasma like unseen tides. Yet amidst all this turbulence, Sagittarius A remains shrouded, like a conductor at the heart of a symphony whose baton sets the rhythm but remains unseen by the audience. From our vantage point roughly 26,000 light-years away, peering through this dense galactic jungle isn't easy. Dust clouds obscure much of the visible spectrum, which is why radio, infrared, and X-ray astronomy are essential. They allow us to penetrate that thick shroud and observe phenomena directly influenced by Sagittarius A's gravitational pull. One of the most fascinating classes of objects orbiting Sagittarius A are the so-called S-stars, or S-cluster stars. These are young, massive stars, many of them blue in color, that inexplicably exist within a fraction of a light-year from the black hole. Given the violent tidal forces at that distance, their presence challenges traditional star formation models. How could stars form in a region where gas is constantly sheared and agitated by extreme gravity? One hypothesis is that these stars were formed farther out in the galaxy and somehow migrated inward, perhaps shepherded by interactions with other stars or large molecular clouds. Another possibility is that two stars collided and merged, forming a massive rejuvenated star in situ. This ongoing debate is more than theoretical. It speaks to the ability of black holes to shape not just the deaths of stars, but their very births. Among these stars, the most famous is S2. This star has been closely monitored for decades, and in 2018, it passed within just 120 astronomical units of Sagittarius A, about 3 times the distance from the Sun to Pluto. During that passage, it reached speeds of more than 7,500 kilometers per second. Observations confirmed key predictions of general relativity, including gravitational redshift. But there may be more hidden in its path, perhaps subtle precessions in its orbit that could hint at the presence of dark matter, or even unseen intermediate black holes lurking nearby. The study of orbits around Sagittarius A has become an entire subfield of astrophysics. Like planets tracing ellipses around the Sun, these stars follow orbits that are gravitationally bound, yet they're perturbed by every ounce of nearby mass, from other stars to invisible clumps of matter. Their motions are celestial fingerprints, each one a subtle map of the spacetime they inhabit. As we refine our measurements and build more sensitive instruments, we may be able to detect variations so minute that they reveal previously hidden components of the galactic center. Another mystery involves the magnetic environment around Sagittarius A. Unlike stellar mass black holes, which often show collimated jets of matter shooting out at near light speed, Sagittarius A seems relatively quiet. It emits radiation, yes, but it does not blast jets into space the way some supermassive black holes in other galaxies do. This raises questions. Why is our central black hole so subdued? Is it because of a lack of available matter to consume? Or is it because magnetic fields around it are not organized in a way that allows jets to form? Recent polarization measurements, especially those captured during the Event Horizon Telescope's campaign, offer tantalizing hints. They reveal that the light near the black hole is polarized, indicating the presence of magnetic fields. The structure of these fields could determine whether material falls straight into the black hole or spirals around it, occasionally being flung outward. Understanding this magnetic topology is crucial, not only for Sagittarius A but for black hole accretion theory in general. And then there's the question of spin. All black holes are thought to possess angular momentum, meaning they rotate, some perhaps at astonishing rates. A black hole's spin affects the shape of its event horizon, the efficiency with which it converts matter into energy, and the orientation of its magnetic field. Yet measuring spin is incredibly difficult. For stellar mass black holes, we often use X-ray emissions from the inner edge of the accretion disk to estimate spin. But for supermassive black holes like Sagittarius A, the task is far more complex. Some indirect evidence suggests Sagittarius A is spinning, though perhaps not at the maximal rate. Its spin axis might even align with the overall angular momentum of the galaxy itself, a potential cosmic fossil telling us about the early formation of the Milky Way. If we can nail down that spin more precisely, we may be able to understand how Sagittarius A has grown over billions of years, whether through steady accretion of material or violent mergers with other black holes. Speaking of mergers, the future of Sagittarius A may involve dramatic cosmic collisions. The Milky Way is on a collision course with the Andromeda Galaxy, expected to occur in about 4 billion years. When that happens, the two galactic cores will begin spiraling toward each other under the pull of gravity. Eventually, their central black holes, Sagittarius A and the one at Andromeda's core, may coalesce into a single, even more massive entity. This cataclysmic event will release a torrent of gravitational waves, rippling across the cosmos at the speed of light. Gravitational waves are one of the most profound discoveries of 21st century physics. Detected for the first time in 2015, they provide a whole new way of observing the universe, not through light, but through the trembling of space itself. While current detectors like LIGO and Virgo are optimized for stellar mass black holes, future space-based observatories like LISA, the Laser Interferometer Space Antenna, will be able to detect the low-frequency waves produced by supermassive black hole mergers. When Sagittarius A eventually merges with Andromeda's central black hole, it will produce gravitational waves that will echo through the universe for millions of years. These waves will carry information not just about mass and spin, but perhaps about the nature of gravity itself. They may help distinguish between general relativity and its possible alternatives, between the known and the unknown. Until then, Sagittarius A continues to sit in silent grandeur, pulling stars into intricate ballets, bending light around its shadowed edge, swallowing particles and information beyond recall. It is a laboratory without equal, one that allows us to study the physics of extremes, to test our theories, to push the boundaries of what is possible. Yet, for all its mystery and might, Sagittarius A also feels oddly familiar. It is our galactic neighbor, our gravitational center, our celestial hearth. We circle it, but in curiosity. We send our minds toward it, armed with equations and instruments, with dreams and data. And as we draw ever closer to understanding, we find that Sagittarius A is not merely a hole in space. It is a wellspring of knowledge, waiting to be tapped. The tale of Sagittarius A is far from over. Even as our telescopes peer ever more deeply into its surroundings, new puzzles emerge. One of the enduring enigmas is the relationship between Sagittarius A and dark matter. The galactic center is thought to be one of the most promising places to detect the elusive substance that makes up approximately 85% of the universe's matter content. While dark matter does not interact with light, its gravitational influence can subtly shape the orbits of stars and gas. Some theorists suggest that Sagittarius A may be surrounded by a spike of dark matter, a dense concentration formed by the gravitational pull of the black hole over billions of years. If this spike exists, it could alter the orbits of nearby stars in measurable ways. Scientists have proposed using the extremely precise motion of S-stars to detect such an influence. Yet so far, the evidence remains inconclusive. A confirmed detection of a dark matter spike would revolutionize our understanding of both galactic dynamics and the nature of dark matter itself. It could even provide clues about the hypothetical particles that constitute dark matter, whether they are WIMPs, weakly interacting massive particles, axions, or something even more exotic. Meanwhile, closer to the black hole, strange structures have been spotted. Radio observations have uncovered linear filaments, thin, bright strands of emission that stretch across the central region like cosmic brushstrokes. Their origin remains a mystery. Some researchers suspect they are related to magnetic fields, or possibly relics of past outbursts from Sagittarius A. These filaments seem to align with magnetic lines of force, suggesting that even in the apparent stillness of the galactic center, unseen energies are at work, shaping and guiding matter in arcane patterns. Then there are the mysterious G objects. First discovered in the early 2000s, these peculiar entities appear to be clouds of gas, or possibly something more complex, that orbit incredibly close to Sagittarius A. One of the most intriguing, dubbed G2, was originally expected to be torn apart by the black hole's gravity during a close encounter. But to the astonishment of astronomers, G2 survived, almost as if it had a dense core hidden within its diffuse gas envelope. This survival prompted a radical rethinking. Could G2 and its kin be something stranger than mere gas clouds? Perhaps they are stars enveloped in thick shrouds of dust and gas, possibly the remnants of stellar collisions or mergers. If so, then G objects might represent a previously unknown class of celestial bodies. They could also offer a glimpse into the complex environment surrounding Sagittarius A, where gravity, radiation, and stellar dynamics combine in unique and unpredictable ways. Let us not forget the human ingenuity required to unlock these secrets. The Event Horizon Telescope, a global network of radio observatories acting in unison, represents one of the most ambitious scientific collaborations in history. When it imaged the shadow of the supermassive black hole in the M87 galaxy, it proved that we could, at long last, see a black hole, not in the traditional sense, but through the gravitational imprint it leaves on light. In 2022, the EHT released its image of Sagittarius A, revealing a fuzzy yet profound ring of emission surrounding a dark void, the silhouette of the event horizon. Capturing this image was vastly more difficult than photographing M87's black hole. Sagittarius A is much closer, but also far smaller in angular size, and it flickers constantly due to dynamic changes in its accretion flow. The EHT team had to assemble data over several days and use sophisticated algorithms to reconstruct an image that matched theoretical expectations. That image is more than a scientific milestone, it is a cultural artifact, a portrait of the invisible, and a reminder of what human beings can achieve when united in purpose. But it is also a stepping stone. The EHT is being upgraded. Future observations may reveal time-resolved images, showing how the material around Sagittarius A swirls and flares in real time. This would allow us to test Einstein's theory of general relativity in its most extreme regime, potentially uncovering deviations that hint at new physics. And while our eyes remain trained on the center of our own galaxy, similar black holes are being discovered in other galaxies, each one a potential laboratory for testing our understanding of the universe. Some of these black holes dwarf Sagittarius A in size, tipping the scales at billions of solar masses. Others may be intermediate mass black holes, an elusive category that bridges the gap between stellar remnants and galactic giants. The discovery of intermediate mass black holes could also help solve the puzzle of Sagittarius A's origin. Did it begin as a seed black hole, growing through accretion and mergers over billions of years? Or did it form in a more sudden and dramatic fashion, perhaps from the collapse of a massive primordial cloud or even a direct collapse black hole in the early universe? The answers to these questions could lie in gravitational waves, in high-energy X-ray emissions, or in subtle motions of stars. And they are not just academic. Understanding how Sagittarius A formed, evolved, and influenced its surroundings can tell us how galaxies themselves come into being, and how life, by extension, is made possible in a universe governed by gravity's dark hand. In a larger sense, Sagittarius A forces us to confront the boundaries of knowledge. It exists at the intersection of what we know and what we do not, a region where classical physics breaks down and quantum theory remains incomplete. The so-called information paradox, whether information swallowed by a black hole is lost forever, remains unresolved, with profound implications for the laws of nature. Some physicists suggest that black holes are not true voids but rather holographic constructs that encode information on their surfaces. Others propose that event horizons may be more permeable than once believed. Still others turn to string theory, loop quantum gravity, or other frameworks in the search for a unifying truth. Sagittarius A is more than an object. It is a crucible, a test, a question posed by the cosmos itself. Every photon that bends around its mass, every star that dances on the edge of destruction, every equation that attempts to describe it, all of them participate in a dialogue that stretches back to the birth of science and forward into the unknown. As we build more powerful telescopes, send spacecraft deeper into space, and refine our understanding of physics, we are not just observing Sagittarius A. We are listening to it, decoding the story it has been telling for over 13 billion years. That story is one of transformation, from dust to stars, from stars to collapse, from collapse to silence, and from silence to understanding. Yet for all our effort, Sagittarius A remains elusive. It is a paradox in motion, both a void and a presence, a destroyer and a creator. It is where time slows, where space curves, where reality frays at the edges. And it is where we, fragile and curious beings orbiting a distant arm of the galaxy, have chosen to focus our gaze. There is something poetic about this. For all our ambition and restlessness, we are anchored by an object that devours light. But in devouring light, Sagittarius A has taught us how to see, truly see, the universe and our place within it. And so, the quest to understand Sagittarius A continues, not just with instruments and equations, but with the sheer force of human curiosity. It is a journey that spans disciplines, blending astronomy, physics, mathematics, and philosophy into a single, unified pursuit. Every step closer to understanding the supermassive black hole at the center of our galaxy also brings us a step closer to understanding the fundamental structure of the cosmos. One of the most profound concepts tied to Sagittarius A is the space-time curvature it creates. According to Einstein's general relativity, mass tells space how to curve, and space tells mass how to move. Nowhere is this relationship more extreme than near a supermassive black hole. Space does not simply bend, it folds, warps, and twists. Time, too, becomes distorted, slowing down for objects nearing the event horizon compared to observers farther away. This is not a theoretical curiosity, it is a measurable, observable phenomenon. Imagine, for a moment, a spaceship sent to orbit near Sagittarius A. To its crew, time would pass normally. But to observers on Earth, their clocks would appear to tick more slowly. This gravitational time dilation has been demonstrated with satellites in Earth's orbit, but near a black hole, the effect becomes dramatic. In fact, this very concept was famously depicted in the film Interstellar, where minutes on a black hole's edge translated to years elsewhere. But even this bending of time is only part of the story. The accretion disk of Sagittarius A, a swirling halo of superheated gas, emits electromagnetic radiation across the spectrum, from X-rays to radio waves. This radiation offers scientists a vital window into the black hole's behavior. The extreme conditions of the accretion disk, where atoms are torn apart and magnetic fields twist violently, provide a natural laboratory for studying matter under conditions impossible to replicate on Earth. Flares from Sagittarius A have been observed regularly, particularly in X-ray and infrared wavelengths. These flares are thought to be caused by magnetic reconnection events, or by clumps of matter falling into the black hole. Studying the timing, frequency, and intensity of these flares helps scientists refine their models of black hole physics. They also hint at the chaotic, dynamic nature of the environment near the event horizon, an environment in which matter dances on the edge of obliteration. Interestingly, the flaring activity of Sagittarius A has varied over time. Historical data from Chandra and XMM Newton space telescopes reveal that the black hole was significantly more active just a few hundred years ago. X-ray echoes bouncing off nearby clouds suggest that it once emitted powerful bursts of energy, miniature quasar-like events. Why it has since quieted down remains an open question. Could it flare up again? Could some unknown process reignite the accretion flow and turn Sagittarius A into an active galactic nucleus once more? This possibility carries implications beyond mere academic interest. An active Sagittarius A could affect the surrounding region of the galaxy. Increased radiation might impact nearby star formation, heat interstellar gas, or even affect conditions in the inner galactic disk. Though our solar system lies some 26,000 light-years from the galactic center, cosmic rays and energetic outbursts can propagate far, subtly influencing the wider galactic environment. Moreover, Sagittarius A sits at the very bottom of the Milky Way's gravitational well. It is the point toward which everything in the galaxy ultimately orbits. The spiral arms, the bar structure, the stars, the gas clouds, all of it revolves around this single, massive anchor. This central role makes it a critical component in modeling the dynamics of the entire Milky Way. When we map out the galaxy's structure, when we simulate its rotation curves, when we analyze the behavior of stars on the periphery, Sagittarius A's mass and influence must be factored in. Any error in estimating its mass, about 4.1 million times the mass of the Sun, would ripple outward, altering our understanding of everything from galactic evolution to dark matter distribution. There is also the tantalizing question of what lies inside the event horizon. The laws of physics as we know them break down at the singularity, the point of infinite density and zero volume at the black hole's core. This is a regime where general relativity and quantum mechanics collide, and we currently have no theory capable of reconciling them. Is the singularity truly a point of infinite curvature, or is it a placeholder for a deeper, quantum reality we don't yet understand? Some physicists believe that singularities may not exist in nature and that quantum gravity effects somehow smear out the core. Others suggest radical alternatives, like the possibility that black holes are gateways to other regions of spacetime, or that they harbor Planck stars, hypothetical remnants where the collapse is halted by quantum forces. Adding to the mystery is the black hole information paradox. According to quantum theory, information cannot be destroyed. Yet classical descriptions of black holes suggest that anything falling into one is lost forever. This contradiction has sparked decades of debate. Is information somehow encoded in the event horizon, as the holographic principle suggests? Could it be retrieved via Hawking radiation, the theoretical process by which black holes slowly evaporate over trillions of years? Or are we simply missing a fundamental piece of the puzzle? Sagittarius A is at the heart of this mystery. As the most accessible supermassive black hole, it provides our best opportunity to test competing theories. The Event Horizon Telescope's future upgrades, combined with next-generation observatories like the James Webb Space Telescope and ESA's Athena X-ray Observatory, promise to sharpen our view even further. But not all insights come from instruments. Theoretical breakthroughs are also vital. In recent years, physicists have explored soft hair theorems, proposed by Stephen Hawking, Malcolm Perry, and Andrew Strominger, as a possible resolution to the information paradox. These suggest that black holes might retain subtle imprints of everything they have consumed, encoded in faint quantum ripples at the event horizon. These ideas remain speculative, but they exemplify the profound nature of the questions Sagittarius A inspires. This is not just a study of one black hole. It is a journey into the very architecture of the universe. And there are still surprises to be found. For example, recent radio observations have uncovered previously unknown structures near Sagittarius A, dense, elongated clouds that may be interacting with the black hole's gravity and radiation. Their nature is unclear. Are they star-forming filaments? Remnants of past outflows? Or something altogether new? Even more intriguing are the recently identified fast radio bursts, FRBs, brief, powerful bursts of radio waves that originate from distant galaxies. While none have been definitively linked to Sagittarius A, similar mechanisms may be at play. Understanding how magnetic fields, neutron stars, and black holes interact could unlock the secrets of these enigmatic signals. Sagittarius A is also helping us understand the nature of time. As Einstein showed, gravity affects time's passage, and nowhere is gravity stronger than near a black hole. By studying how time behaves in the vicinity of Sagittarius A, scientists are refining their models of time dilation and space-time curvature. These insights have real-world applications, from improving GPS satellites to informing theories of cosmic expansion. As we reach deeper into these mysteries, we must also consider our own philosophical position. Why are we so drawn to the galactic center? What compels us to study a region we can never visit, whose very nature defies comprehension? The answer lies in our nature as seekers. Sagittarius A represents a frontier, not just in space, but in knowledge. It challenges our intellect, our instruments, and our imagination. It beckons to us from the depths of the cosmos, whispering of truths beyond the horizon of what we know. And so we continue to look, to listen, to calculate, to dream. We send signals across the void, we chart the dance of stars, we chase flares through radio waves and X-ray pulses. We decode the echoes of past eruptions, seeking to reconstruct a story billions of years in the making. What we have learned so far is staggering. What remains to be learned is even greater. The gravitational pull of Sagittarius A governs the orbits of stars swirling in close proximity, creating a celestial ballet that offers astronomers invaluable clues to its nature. Among these stars, the S stars, a cluster orbiting within a mere fraction of a light-year from the black hole, have been studied extensively over the past few decades. Their orbits are not only incredibly fast but also highly elliptical, allowing scientists to test general relativity in the strong gravitational field regime. Observing their trajectories reveals subtle shifts predicted by Einstein's theory, such as gravitational redshift and perihelion precession, phenomena that are minute yet measurable with today's technology. The star S2, in particular, has played a pivotal role. Completing an orbit every 16 years, it swoops perilously close to Sagittarius A, moving at speeds exceeding several thousand kilometers per second at its closest approach. Tracking S2's journey has allowed scientists to observe the effects of gravitational time dilation in real time and confirm that the immense mass at the galactic center indeed behaves as a supermassive black hole should according to general relativity. The 2018 pericenter passage of S2 was a landmark moment, where high-precision spectroscopy measured the redshift of its light as it experienced the black hole's gravity, directly confirming the relativistic predictions. Yet the environment surrounding Sagittarius A is far from static. Dense clouds of gas and dust swirl around in complex patterns, some forming the bright accretion disk while others orbit more distantly. This environment is turbulent, shaped not only by gravity but also by magnetic fields and energetic events like stellar winds, supernova explosions, and interactions with the black hole's radiation. The interplay between these forces creates a dynamic ecosystem in the galactic core that affects star formation, black hole feeding, and the distribution of matter. Recent discoveries have also revealed a population of enigmatic objects known as G-objects, compact, dust-enshrouded entities that behave somewhat like stars but defy easy classification. These objects move along highly eccentric orbits that bring them close to Sagittarius A, and their nature remains mysterious. Some hypotheses suggest they could be the remnants of stellar mergers, stars cloaked in gas and dust, or even protostars in the process of formation. Their discovery has added another layer of complexity to our understanding of the galactic center and the processes operating in such an extreme environment. One particularly interesting feature associated with Sagittarius A is the Fermi bubbles, massive, balloon-like structures emanating from the Milky Way's center, extending tens of thousands of light-years above and below the galactic plane. These enormous lobes, discovered in gamma-ray observations, are thought to be relics of past energetic outbursts from the black hole or bursts of star formation activity. They provide evidence that Sagittarius A's activity has fluctuated dramatically over cosmic time, alternately quiet and violent. Studying these bubbles helps researchers understand the feedback processes that regulate the growth of galaxies and their central black holes. The immense gravitational forces near Sagittarius A also offer a natural laboratory for extreme physics beyond what can be recreated on Earth. The intense gravity, high temperatures, and strong magnetic fields create conditions where plasma physics, relativistic jets, and high-energy particle acceleration converge. Scientists study the synchrotron radiation emitted by relativistic electrons spiraling in magnetic fields to probe these environments. These processes are linked to phenomena seen in active galactic nuclei across the universe, making Sagittarius A a nearby prototype to understand black hole-driven activity on a cosmic scale. Technological advancements in radio interferometry, such as those utilized by the Event Horizon Telescope, have pushed the boundaries of resolution to unprecedented levels, allowing for the imaging of structures mere microarcseconds across. These instruments stitch together data from radio telescopes spread across the globe, synthesizing a virtual Earth-sized telescope capable of peering into the heart of our galaxy. The first image of the black hole in the galaxy M87 demonstrated this capability spectacularly. While imaging Sagittarius A presents unique challenges, including its smaller size, variable emission, and scattering effects from interstellar material, efforts are underway to achieve a similarly detailed image, which would reveal the shadow of the event horizon and the dynamics of matter at the brink of oblivion. Theoretical modeling complements observational efforts by simulating how matter behaves under extreme gravity, helping interpret the complex data collected. General relativistic magnetohydrodynamic (GRMHD) simulations depict the flow of plasma and magnetic fields near the black hole, predicting the shape and behavior of the accretion disk, jets, and radiation patterns. These simulations are crucial for comparing observed data with physical expectations, refining our understanding of black hole physics and accretion dynamics. Sagittarius A also intersects with fundamental questions in cosmology. Its presence and mass fit within broader models of galaxy formation and evolution. Supermassive black holes appear to be ubiquitous in the centers of large galaxies, their masses correlating with the properties of the host galaxy's bulge. This correlation hints at coevolutionary processes where black holes and galaxies grow together, influencing each other through feedback mechanisms such as outflows and radiation pressure. Understanding Sagittarius A thus contributes to the grand narrative of how galaxies like the Milky Way came to be. Despite its importance, Sagittarius A remains elusive in many respects. Its relative quiescence compared to more active galactic nuclei puzzles astronomers. Why does it currently consume matter so slowly, emitting comparatively little radiation? Is it starved of fuel, or is the accretion process somehow inefficient? Could periodic bursts of activity lie ahead, triggered by infalling gas clouds or stellar disruptions? Moreover, Sagittarius A challenges our understanding of black hole growth over cosmic timescales. How did it accumulate millions of solar masses in the first place? What was its seed? A massive star collapse, or a direct collapse of a primordial gas cloud? These questions link to the broader field of black hole formation in the early universe, where supermassive black holes have been detected at surprisingly young cosmic ages, posing challenges to existing theories. In addition to the black hole itself, the galactic center hosts exotic objects like pulsars and X-ray binaries. Detecting pulsars near Sagittarius A has been difficult due to scattering and absorption by the dense plasma in the region, but their discovery would open new avenues for precise gravitational tests and measurements of space-time properties. Pulsars act as highly stable cosmic clocks, making them ideal probes of gravity in extreme conditions. The study of Sagittarius A also intertwines with efforts to detect gravitational waves, ripples in space-time produced by massive accelerating bodies. While current detectors like LIGO are tuned to stellar mass black hole mergers, future space-based observatories such as LISA aim to detect lower-frequency waves emitted by supermassive black hole mergers and interactions. Although Sagittarius A is relatively isolated now, its future collisions with other massive black holes as galaxies merge will produce powerful gravitational waves, adding a dynamic chapter to its history. Beyond pure science, the cultural and philosophical implications of Sagittarius A are profound. This invisible, immensely powerful object at the heart of our galaxy inspires awe and wonder, challenging humanity's place in the cosmos. It evokes questions about the nature of existence, the limits of knowledge, and the fate of matter and information in the universe. From ancient stargazers who first mapped the Milky Way to modern astronomers deploying cutting-edge technology, Sagittarius A has always been a symbol of the mysterious and the unknown. As our observational capabilities continue to grow, so too will our understanding of Sagittarius A. From radio waves to X-rays, from gravitational waves to theoretical models, the coming decades promise a richer, deeper insight into this cosmic enigma. Each discovery will not only illuminate the nature of the supermassive black hole, but also cast new light on the fabric of the universe itself. The story of Sagittarius A is far from complete. It is a living, evolving narrative, an intersection of astrophysics, technology, philosophy, and human curiosity. As we gaze into the heart of our galaxy, we are looking not only at a monstrous singularity, but at a mirror reflecting the grandeur and mystery of existence itself. Sagittarius A remains a captivating subject not only because of its extraordinary physical properties, but also due to the broader cosmic questions it helps us address. One of the most intriguing mysteries revolves around the nature of the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational grasp. This boundary marks a point of no return, an enigmatic frontier where our current understanding of physics begins to break down. Theories such as quantum gravity and string theory attempt to reconcile the classical description of black holes with the quantum mechanics governing the subatomic world, but the event horizon stands as a testing ground for these ideas. At the core of this puzzle is the so-called information paradox. According to classical theory, any information about matter crossing the event horizon is lost forever, violating the principles of quantum mechanics which assert that information cannot be destroyed. This paradox has sparked decades of debate and theoretical development, with proposals such as the holographic principle suggesting that information may be encoded on the event horizon's surface in a manner analogous to a hologram. Sagittarius A, as the closest supermassive black hole, offers a natural laboratory to study these fundamental questions, potentially bridging the gap between general relativity and quantum mechanics. Observationally, the variability of Sagittarius A's emissions across the electromagnetic spectrum provides clues about the physics operating near the event horizon. While the black hole is generally quiescent compared to active galactic nuclei, it exhibits sporadic flares in X-rays and infrared light. These flares may result from magnetic reconnection events, sudden accelerations of charged particles, or the tidal disruption of smaller bodies venturing too close. Monitoring these flares over time helps scientists probe the environment's dynamic processes, magnetic field configurations, and the mechanisms by which energy is released near the black hole. In addition to electromagnetic observations, advances in high-energy astrophysics and neutrino astronomy are beginning to shed light on Sagittarius A's energetic processes. Neutrinos, nearly massless particles that rarely interact with matter, can escape dense astrophysical environments unscathed, carrying information about particle acceleration mechanisms near black holes. Detecting neutrinos originating from Sagittarius A would provide a new perspective on the high-energy phenomena at the galactic center and potentially link black hole physics with cosmic ray production. The dense star cluster surrounding Sagittarius A is also a site of ongoing stellar evolution under extreme conditions. Stars in this region are subjected to intense tidal forces, radiation, and gravitational interactions that influence their life cycles. Some stars may undergo unusual evolutionary pathways, such as being stripped of their outer layers or merging to form massive, luminous objects. Studying these stars contributes to our understanding of stellar dynamics, star formation, and the interplay between black holes and their stellar environments. Furthermore, the presence of molecular clouds and dense gas reservoirs near Sagittarius A suggests that the galactic center could be a cradle for star formation despite the hostile conditions. Observations reveal complex filamentary structures and shock fronts where gas is compressed, potentially triggering the birth of new stars. The balance between black hole feedback, through radiation, jets, and winds, and the gravitational collapse of gas clouds shapes the star formation rate, influencing the evolution of the Milky Way's core. The role of magnetic fields in the vicinity of Sagittarius A is another crucial aspect. These fields are believed to channel the inflow of matter, regulate accretion rates, and launch relativistic jets. Polarization measurements of the emitted radiation provide insights into the strength and orientation of these magnetic fields, offering clues about the mechanisms powering the black hole's activity. Understanding magnetic fields near supermassive black holes has broader implications for galaxy evolution, as they mediate energy transfer on vast scales. Sagittarius A's relatively low luminosity compared to active supermassive black holes in other galaxies raises questions about the duty cycle of black hole activity. It is possible that our galactic center is currently in a dormant phase, with past episodes of intense accretion leaving behind structures like the Fermi bubbles. This cyclical behavior may be common among galaxies, with black holes fluctuating between active and quiescent states depending on the availability of gas and environmental factors. Studying these cycles helps unravel the history of the Milky Way and the coevolution of its central black hole. From a cosmological perspective, Sagittarius A offers a window into the formation and growth of supermassive black holes across cosmic time. Theories about the origins of these giants range from the collapse of massive primordial gas clouds in the early universe to the mergers of smaller black holes and stellar remnants. Observations of distant quasars reveal supermassive black holes existing less than 1 billion years after the Big Bang, posing challenges for formation models. Understanding Sagittarius A's growth history and environment provides a local benchmark for these broader questions. The galactic center's extreme conditions also serve as a proving ground for tests of fundamental physics. Precise measurements of stellar orbits and timing of pulsars can test predictions of general relativity and alternative gravity theories. Deviations from expected behavior could hint at new physics beyond Einstein's framework, potentially illuminating the nature of dark matter, dark energy, or quantum gravitational effects. Sagittarius A thus acts as both a cosmic laboratory and a gateway to uncovering new physical laws. On the technological frontier, upcoming observatories and instruments will revolutionize our ability to study Sagittarius A. Facilities like the James Webb Space Telescope, next-generation very large telescopes, and enhanced radio arrays will offer unprecedented resolution, sensitivity, and spectral coverage. These capabilities will enable detailed mapping of the black hole's immediate environment, tracking of transient phenomena, and the detection of faint signals previously beyond reach. Combined with advances in computational modeling and data analysis, these tools promise a transformative era in our understanding of the Milky Way's heart. The narrative of Sagittarius A also intersects with the human experience of exploration and discovery. The quest to understand the black hole at the center of our galaxy reflects humanity's enduring desire to comprehend the universe and our place within it. This journey spans centuries of scientific progress, from early astronomical observations to cutting-edge physics, blending curiosity, ingenuity, and imagination. As we continue to unravel the mysteries of Sagittarius A, we deepen our connection to the cosmos and to the fundamental questions that define our existence. In essence, Sagittarius A is far more than a singularity cloaked in darkness. It is a dynamic, complex, and fascinating object whose study touches on diverse fields: astrophysics, cosmology, particle physics, and philosophy. Its gravity shapes the motion of stars, its radiation illuminates processes at the edge of spacetime, and its presence anchors the structure of our galaxy. The exploration of Sagittarius A represents a monumental chapter in humanity's quest to understand the universe, revealing both the limits of current knowledge and the vast potential for future discovery. The story of Sagittarius A is ongoing, its depths still largely unexplored, inviting continued observation, theorization, and wonder. As technology advances and our theoretical frameworks evolve, the secrets locked within this supermassive black hole will gradually come to light, enriching our understanding of the cosmos and the fundamental nature of reality itself. Sagittarius A continues to captivate scientists because it embodies one of the most extreme environments in our universe. It's an environment where gravity warps spacetime to extraordinary degrees, where matter is crushed to densities unimaginable on Earth, and where light itself is trapped, offering a glimpse into the deepest mysteries of physics. The study of Sagittarius A not only helps us understand the mechanics of black holes but also challenges and refines the fundamental theories that describe our universe. One of the essential features of Sagittarius A is its immense mass, estimated to be around 4 million times that of our Sun. This staggering mass is confined within a region no larger than our solar system, making the density of this object extraordinarily high. The very concept of such concentration of mass forces scientists to explore how matter behaves under such extreme conditions. Classical physics breaks down at the event horizon, the boundary marking the point beyond which no information or matter can escape. Here, relativistic effects dominate, and quantum mechanics may play an integral role in the true nature of the black hole. Observing Sagittarius A directly is an enormous challenge due to the dense clouds of gas and dust obscuring our view from Earth. This is why astronomers employ a range of techniques across the electromagnetic spectrum, from radio waves to X-rays, to penetrate these veils and reveal the phenomena at the galactic center. Radio astronomy has been particularly instrumental because radio waves can pass through dense interstellar material, allowing telescopes such as the Very Large Array and the Atacama Large Millimeter/Submillimeter Array, ALMA, to capture detailed images of the region around Sagittarius A. A landmark achievement in the study of Sagittarius A was the use of very long baseline interferometry, VLBI, a technique that combines signals from widely separated radio telescopes to simulate an Earth-sized telescope. This technique culminated in the Event Horizon Telescope collaboration, which produced the first-ever image of a black hole's event horizon, not Sagittarius A itself, but a similar supermassive black hole in the galaxy M87. This achievement laid the groundwork for future observations aimed directly at Sagittarius A, promising images that will provide more direct insights into the structure and behavior of our own galactic center. The gravitational influence of Sagittarius A is so profound that it shapes the orbits of nearby stars in remarkably predictable ways. Over decades of observation, astronomers have tracked the motions of stars such as S2, whose highly elliptical orbit around Sagittarius A takes approximately 16 years to complete. The precise tracking of these orbits has confirmed predictions of Einstein's general relativity with incredible accuracy, including the gravitational redshift, the shifting of light to longer wavelengths as it escapes the intense gravity of the black hole. These measurements provide compelling evidence that a supermassive black hole occupies the heart of the Milky Way. Despite its immense gravitational pull, Sagittarius A is relatively quiet compared to the monstrous black holes that power quasars in distant galaxies. Its low luminosity suggests that it is currently in a state of low accretion, swallowing matter at a relatively slow rate. However, this quiet state is not permanent. Evidence suggests that Sagittarius A has undergone periods of much greater activity in the past, as indicated by phenomena such as the Fermi bubbles, giant lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane. These bubbles may be relics of past energetic outbursts from Sagittarius A, revealing the dynamic nature of its feeding cycles. One area of active research concerns the accretion disk around Sagittarius A, the swirling maelstrom of gas and dust spiraling into the black hole. The physics of accretion disks is complex, involving magnetic fields, turbulence, and relativistic effects. This disk emits across a wide range of wavelengths, providing astronomers with clues about the processes governing the inflow of matter and the release of energy. Understanding the structure and behavior of the accretion disk is critical for building comprehensive models of how supermassive black holes grow and influence their surroundings. Magnetic fields near Sagittarius A also play a crucial role in shaping its environment. These fields can channel and accelerate particles, producing jets of energetic plasma that shoot out at near-light speeds in some black holes. Although Sagittarius A does not currently exhibit strong jet activity, faint radio emissions hint at past or intermittent jet production. Studying these magnetic phenomena enhances our understanding of the mechanisms that convert gravitational energy into powerful emissions, which can affect star formation and the evolution of the galactic nucleus. Beyond electromagnetic signals, gravitational waves are an emerging frontier in the study of black holes. These ripples in spacetime, first predicted by Einstein and directly detected in 2015 by LIGO, offer a new way to observe black hole interactions. While current detectors are most sensitive to stellar mass black hole mergers, future space-based observatories such as the Laser Interferometer Space Antenna, LISA, will target supermassive black holes like Sagittarius A. Detecting gravitational waves from the galactic center would open unprecedented windows into the dynamics and merger history of our galaxy's core. The environment around Sagittarius A is not just a site of black hole activity, but also a bustling stellar ecosystem. The nuclear star cluster surrounding the black hole contains a diverse population of stars, including massive young stars, old red giants, and exotic objects like pulsars and X-ray binaries. These stars experience extreme gravitational forces, leading to phenomena such as tidal disruption events where stars wander too close to the black hole and are torn apart. Observing these interactions provides insights into both stellar evolution and the behavior of matter under the influence of strong gravity. One of the more fascinating prospects is the discovery of pulsars, rapidly rotating neutron stars emitting beams of radio waves, in close orbits around Sagittarius A. Pulsars serve as extraordinarily precise cosmic clocks, enabling tests of gravitational theories with exquisite sensitivity. Despite intensive searches, only a handful of pulsars have been found near the galactic center, likely due to scattering and absorption by intervening material. However, continued advances in radio astronomy and signal processing may soon uncover more pulsars, enabling new experiments probing the black hole's gravitational field. The study of Sagittarius A also intersects with questions about dark matter, the elusive substance making up most of the universe's mass but detectable only via its gravitational effects. The dense central region of the Milky Way is thought to harbor significant dark matter concentrations, which influence the dynamics of stars and gas. Understanding how dark matter interacts, or doesn't interact, with black holes may shed light on its nature and distribution, with Sagittarius A providing a key observational anchor for these investigations. In addition, the chemistry of the galactic center region is remarkable. High-resolution spectroscopy reveals complex molecules and unusual chemical abundances in the molecular clouds surrounding Sagittarius A. These chemical signatures result from interactions between intense radiation, shocks, and cosmic rays emanating from the black hole's vicinity. Studying this chemistry not only informs us about star formation processes under extreme conditions but also about the feedback mechanisms linking black hole activity and galactic evolution. As our technological capabilities advance, the prospects for studying Sagittarius A become ever more exciting. The upcoming generation of telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, promises to deliver unprecedented detail and sensitivity. These instruments will enable imaging of the event horizon, mapping of magnetic fields, and detection of faint signals from stars and pulsars near the black hole. Coupled with advances in computational astrophysics, these observations will refine theoretical models and possibly reveal new physics. Sagittarius A offers a profound philosophical and cultural symbol. It represents the ultimate frontier of knowledge, the boundary between what we can observe and what remains hidden. Its study challenges human intellect and imagination, inspiring generations of scientists and enthusiasts alike. As we peer into the heart of our galaxy, we confront fundamental questions about the origin, structure, and destiny of the cosmos. Questions that resonate beyond science into the realm of human wonder. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.